Krishnan. He wrote a book on this switched reluctance machine and its control applications. Yeah. So, what is the speciality of this switched reluctance machine? So, just let me briefly just glance through. So, the switched reluctance machine, in fact, it's a very simple and rugged in construction, and which is suitable for very high speed operation. So, and its power density capability is too good, and and the main advantage in this machine as compared to other counterparts is say this in this the rotor doesn't have any conductors and the permanent magnet. Application for which this machine can be used. And here, basically, when I say this switched reluctance machine, the term switched reluctance electronic actuators for each phase winding will be designed with, and it comes with, in fact. So, therefore, the switched reluctance means here the switching of the phase currents. Switching of the phase currents, which is an essential aspect of the operation of the switched reluctance motor. So that is where, of course, this so that is why this machine is so called a switched reluctance machine. Okay, and this switching is more precisely called a commutation. Of course, the word commutation is most commonly okay. So it is heard for our in our electronics circuits. And so the electronically commutated reluctance motor is perhaps an even more precise term than the switched reluctance motor. So that's the thing, like, and its operation basically depends on the flux linkage characteristics, and that is a one speciality, and it's also it's not a straightforward mechanism to devise this flux linkage characteristic of this machine, where this needs a special kind of a evaluation and the determination of this flux linkage characteristics, and therefore. And here this, see, this is like a simple constructional view of this switched reluctance machine. Here, if you look at this, the view, see, this is something like 8 by 6 combination. So here we have the 8 stator poles and the 6 rotor poles. Okay, so accordingly, so now for each stator phase winding, okay, so we need to have one actuator for each leg, so for each phase, okay, and then what is it? This flux linkage characteristic. If we look at this flux linkage characteristic, here. Okay. So this flux linkage characteristic is depending on the various rotor position. It depends. So this flux it varies depending on the position of the rotor, and determining that position of the rotor is very important. Therefore, the position sensor play a very vital role in estimating the particular position, and with respect to that the flux linkage characteristics with respect to that particular position, it can able to estimate. So that is the thing. So it means that the phase current, the flux linkage, it varies with this as a function of current. Okay, and for every position, see if you look at this. The first, see, it is like aligned position. Aligned in the sense, see, this rotor poles is aligned exactly okay, to this stator poles. If you look at this here, this, what is that, phase C poles, those are the aligned poles now in this particular view. So then other rotor poles are unaligned with respect to the stator poles. Okay. So with this, like, no, for every aligned position, this okay, the flux linkage is okay. It varies in this way. But otherwise, if it is of intermediate position, so then see the flux linkage characteristic changes as a function of current, and again this unaligned position. See, this looks more or less. I think not exactly, but more or less linear at the unaligned position. Okay, the flux linkage behavior. But whereas for this other than this unaligned position, say this flux linkage is not the linear function. Okay, so therefore the control of this switched reluctance motor is not okay straightforward, and it needs a very okay say the effective controller that we need to design with. And also this rotor position need to be sensed. For that a feedback system is required, and depending on that the controller parameters need to be designed with. So anyway, and then if you look at this profile, this is the inductive rotor. So depending on the rotor position, this inductive profile of this machine will also change. See, this LU, this indicates what is this unsaturated inductance with respect to this unaligned position, whereas this LA is the unsaturated inductance in aligned position. So that means this is how from unaligned to aligned position the inductor profile is changing. Okay, and here you see. See, this rotor is aligned when diametrically opposite stator poles are excited. As I say, okay, if you look at this for this aligned poles, whenever this rotor pole is aligned, okay, and they are diametrically opposite stator poles, they are excited in a magnetic circuit. This rotating member prefers to come to the minimum reluctance position at the instant of excitation, while two other rotor poles are aligned to the two stator poles. Another set of rotor poles is out of alignment. Say that means other set of rotor poles are unaligned position, but only that one set of rotor poles is aligned with the stator. Okay, so therefore then this set of stator poles is excited, whichever that okay that aligned with. So to bring the rotor poles into the alignment. Okay, so likewise the sequentially the switching the currents into the stator windings that leads to the rotation of the rotor, that makes the rotor to rotate. Okay, so the moment of the rotor ends, that produces the torque, okay, and power. So that involves means what is that we need to understand. This involves the operation of this switch, SRM motor, that involves the switching of currents into the stator windings. So when there is a variation of this currents into the stator windings when there is a variation of reluctance. So therefore, this variable speed motor drive is referred to as this switched reluctance motor drive. Hence, this is very widely used for like say this say applicable for the wide variable speed applications. Okay. And if you look at this comparison with the switched reluctance and the synchronous reluctance. So here the switched reluctance in this, both the stator and rotor have the salient poles. Hence, this switched reluctance motor is also called as a doubly salient machine. Okay. But whereas this synchronous in this other synchronous counterpart, the stator has a smooth bore except for slotting, okay, but not like in the SRM. Then the other second point is the stator winding comprises a set of coils, and each of which is wound on one pole, okay. And whereas in the synchronous, the stator has a polyphase winding with approximately sinusoidally distributed coils, okay, in the synchronous reluctance machine. And in the the point 3 is that excitation is a sequence of current pulses applied to each phase in turn, whereas in the synchronous reluctance machine, the excitation is a set of polyphase balanced sinusoidal currents, okay. But here it's not the sinusoidal currents in case of a switched reluctance machine, okay. Yeah. And the other difference is that as the rotor rotates, the phase flux linkage should have the triangle or sawtooth waveform, but not vary with the current. Whereas with respect to the synchronous reluctance counterpart, the phase self-inductance should vary sinusoidally with rotor position, but not vary with the current. So means this is the difference. Because see, these currents are sinusoidal in nature, but whereas here in this currents are not sinusoidal in nature in the case of a switched reluctance machine. So for that matter, now see we have the different types of the combinations, okay, of the depending on the different combination of the stator and the rotor poles. This switched reluctance machine is classified, okay, it can be classified into the various type, like various combinations. So, so here see the various possible combinations or configurations is 12 by 6, 10 by 6, 8 by 6, 6 by 4 and 4 by 2. So these are the various possible combinations of this switched reluctance machine. So it means that here in this first one, if you look at this 4 by and here stator poles are 8, hence because the stator windings are excited in fact, okay. So therefore say this is of like a 4-phase machine, 4-phase, okay, machine. And similarly the 4 rotor poles and 6 stator poles means it is like a 3-phase SRM. And this 8 by 10 means it is of like 5-phase, because the 10 stator poles, no. So obviously this is like a 5-phase motor, okay. So it needs the 5-leg converter, okay. So means depending on the number of phases, that many legs of this power electronic converters, okay, that is required. So that is how these SRM configurations can be evolved. And this okay, suppose if I say this 12 by 6, 12 by 6 means it could be like a 6-phase, because the 12 stator poles and the 6 rotor poles. So therefore as it is stator poles are 12, so the number of phases is 6 phase, okay. So like that the different configurations of this SRM can be okay, classified. And also then the, see, as I mentioned, it is a W salient motor, because both the stator and the rotor poles are of salient in nature, and no winding and permanent magnet on the rotor, because that is the best part and the advantage of the SRM machine. And also, like see, as like our DC motors, DC machines, so this SRM doesn't have any brushes or commutators, all these things, because this commutation is now, it is with the help of our, okay, power electronic actuators only, okay. So that depends on our switching pattern, okay, switching technique. So therefore, there is no need of commutators and brushes or any other slip rings like in a kind of a AC motors. So therefore, so this machine makes more special as compared to the other machine counterparts. So therefore, see, the size and cost of a machine is also significantly less. Okay, that is where the best part of this switched reluctance machine. But only thing, see, there are some other complexities are there. See, that is where, of course, but here this needs a very systematic control with rotor feedback, okay, rotor position feedback, and this estimation and deciding of this rotor position angle, position angle is also a see, the one main important task where we need to do this rotor angle estimation. Accordingly, the switching pulse can be developed or realized. So therefore, that advantage, the advantages of this motor can be listed like this. So this is like a simple and rugged construction, simple winding and insulation. Okay, simple in winding, but otherwise, and also it is more economical, as I mentioned, like, because it doesn't have any brushes or commutators. Okay, all these things, it makes a more compact size, but with high power capability. Okay, and for high speed ranges, and also, of course, we can do design a, as it is a like a converter activated machine. So we can design like a fault tolerance mechanism for the safety purpose of the drive, and moreover, therefore, considering all these factors, this can provide the good efficiency and also the high torque to inertia ratio. Okay. And then it also provides the more thermal robustness. Okay. And but otherwise, when we use these power electronics converters, the switching frequency, of course, here because we know that the switching frequency is related to some kind of a switching pattern in the PWM process. Okay, but that leads to the as the switching frequency increases, switching losses will increase. So therefore, it is not that advisable like in a DC to DC converters. So we no need to go for very high switching frequency also here, but otherwise, so moderately, so we can go for like a inverter grade switching frequency, like what we use like in a case of a VSI and CSI inverters for induction motor. Okay, so yeah, so like that. Otherwise, in at the same time, suppose even if you go for higher switching frequency, we can also just say we can devise a mechanism of like soft switching mechanism. So if possible, so that way the switching losses can also be minimized. Okay, to the extent possible, if possible. So that kind of features is also possible. Okay, and but the complexity is here. The disadvantages are the modeling of this machine is very complex, because it is because of the flux linkage behavior with respect to the current, okay, the phase currents. So they are non-linear in nature. So because of this non-linear flux linkage characteristic behavior of this machine, the modeling of this machine is it's not that straightforward, but it's quite complex. And see, it needs a lot of iterations. Even suppose if I want see for every rotor position, I need to estimate this. Okay, the what is it? This what is flux linkage behavior with respect to the different rotor positions. And for that, even the conditioning is required. That sensing feedbacks. Okay, to sense the position of the rotor. So we need a okay feedback system. And see here, therefore, that shaft position sensor is essential here in this case. Okay, and other thing is that the torque production has a pulsating nature, leading to a torque ripple. This is the most disadvantage factor. That is where, of course, this machine could not take much. In a prominent role in the most of the at present, but otherwise there's a lot of research is going on, especially on this aspect. So like how to reduce the torque ripple, because that leads to the very high noise okay in the machine. So because of this, so this motor is limited to for very few applications at present. But otherwise, if we just overcome this kind of, okay, if we minimize this torque ripple and hence the noise, so this motor becomes a more apt and more advisable for a very the large variety of applications, wide applications in fact, because now we are talking about the EV machine, electric vehicles. So for this electric vehicles, because it doesn't have any the brushes and commutators, all these things. So obviously it's a very good option rather than like a so the other machine counterparts. Okay, so that it makes more cost effective and most robust and okay, all these things. So therefore, and yeah, that's what, unlike AC or DC machines, it cannot run on online supply. It requires the power inverter to drive, like, because it's not like a, see, I cannot connect the direct power supply, like, okay, so to the motor windings, but it is through a power electronic actuators, okay, power electronic switch. So hence, see, obviously that makes more okay space consumption for the converter, and moreover it is like see, this converter need to be operate with the switching operation, like, okay, for that we need to design a specific pulse control mechanism. So that is another complexity. So, but anyway, that we cannot forego, that we cannot, because it's the inherent behavior of this switched reluctance machine. So, which is in which the converter is essentially, it is an essential part of the SRM drive. Okay, but otherwise, the major disadvantage is the torque ripple. Okay. So because these phase currents are highly pulsating in nature, okay, so because of that, because the torque is also a function of current, if the current is pulsating in nature, obviously the torque is also pulsating in nature, okay, so that is one thing. And say because of this switching operation, even this also needs to the noise, okay, large amount of noise. Because if you see the SRM, if you compare the noise behavior of the SRM machine with the other counterparts, so this produces a lot of noise. Okay, it is because of high torque ripple behavior. Okay, so that, so if you can able to counter these two disadvantages, see this machine could be a very best option for wide range of applications, okay, with high power density and okay, wide high speed range as well as high torque capability. And see, when it comes to the applications, I already mentioned, like, okay, so compressors, fans, pumps, centrifugal pumps, and also the domestic drives, okay, food processor, washing machine, vacuum cleaners, electric vehicle applications, aerospace applications, servo drives, okay, whatnot. So there could be several applications which we can use, but only thing is that, say, some demerit factors we need to see address for this machine. Otherwise, so this is very well suitable for various applications, okay, and it's a very good option as compared to the other machine counterparts. And what is the significance of control technology? Here the control, say the machine dynamics and its response to this applied load means that designing this control, okay, controller is a tedious process here. And anyway, see, because even say why I am telling is that, see, right from the initial starting to the normal steady state operation of the machine, so this involves this control mechanism dynamics, okay, that's very crucial part here. So that I'll just discuss about that, what is that initial the low speed operation and the high speed operation desirability of this machine operation. And say, and then this power can come, of course, anyway. So that's a power electronic converters, it's an essential part of the machine, and wherein which this control scheme, control technique is, again, it's important. And protect the motor and controller itself from the damage means where, say, it talks about now we can say the protection and safety of the machine, so which can be resolved by means of some kind of a techniques, fault tolerant techniques, okay. So by devising this appropriate fault tolerant converter topologies, inverter topologies, okay. So that, so we can make the drive is more safer and this thing. And this, these are the, of course, this is a mathematical model. Simple, it looks to be very simple, but here what is that I wanted to just focus here on that. See if we can see this, the flux linkage. No? The flux linkage is changing with respect to this rotor position. That is how this machine characteristics becomes more non-linear. So if the system becomes more non-linear, the effort of this control, okay, the control effort is, okay, it requires more effort, okay. So that is what the say this mean, because the main, this switched reluctance machine main characteristic operation, it mainly depends on the characteristic behavior of the flux linkage, okay. So which these are very highly non-linear in nature. So it means that see the here these are the various variables, as okay, we can rightly understand from this, okay. So it's a simple okay, KVL equation if you apply like that. See, but in this way you see the V is voltage, I is the phase current, and R is the phase resistance. Of course, any windings, phase windings will have their own resistance. We cannot just forego those things. And phi is the flux linkage of the winding, and L is like it is the incremental inductance. So okay, and these are the various other parameters like speed, position in degree, okay. So in case if you neglect the saturation, if saturation is neglected, then this flux linkage so comes out to be like it's a function of, okay, it's a product of current and this inductance. That means even inductance is also changing, okay. So you see this IL is also a function of the rotor position. So therefore that inductor profile is changing linearly from unaligned position to the aligned position, okay. So that will happen, see, that's common for both, whether in the motor operation or the generator operation. So I wanted to mention, like other similar, all other machines, this machine can also be operated either as a motor or a generator, okay. So that yeah, And see, as this SRM switched reluctance machine can also operate as a motor as well as a generator, and in specific this SR generator becomes more prominent for some of the applications like a wind energy conversion and solar PV, even the PV, okay, direct PV integration, okay, because the required source is the DC excitation, not the AC. So therefore, say that makes more suitable for the various wide standalone off-grid applications also. So therefore, now here this the principle of operation, this mainly depends on this co-energy principle. Okay, so this is the mathematical model. Okay, anyway, this is well available in the all resources. But what I mean to say, this say what is it? This machine works in the principle of this co-energy. So that's what I wanted to say. And here, if you look at this torque equation, you see the function current is the square of the current. It means that even what does it mean, this I square? So even means this torque also it becomes more nonlinear, na? It's a nonlinear, say I square, and dl by dt here. Okay. So therefore, this nonlinear function of current it is. Torque is also a nonlinear function of the current. It's not a linear function. And also, moreover, it is depending on the direction of the current as well. But however, irrespective of the, what is this? The direction of the current, because this torque is a direct function of the current, in fact, but no, even though of course it is the square of the current, nonlinear function of the current, but because of this square nature, this sign depends on the slope of the inductance profile, and moreover, you see, but irrespective of the direction of this current, the torque is always positive. So that is what we can just understand from this. But otherwise, the sign depends on the slope of this inductance profile also, because that means the positive torque can be generated. But here I cannot see the current can be of any direction, but it makes a positive function, right? But however, this dl by dt, this inductive profile, so here this positive torque can be generated, because for the to justify the motor and generator operation. So how do we need to justify? Because this torque, what could be the torque behavior of the motor and the generator like? So what can here see this positive torque can be generated when the inductance slope is positive with respect to the rotor position, and negative torque when it is when the slope is negative. So that is how. So this describes the operation of the motor operation and the generator operation. If the slope of the inductance is positive in nature, then it is a motor operation. If it is of negative, then it's like generating operation. So here you can just we can see clear the same principle here. Okay, so that means in the under motor operation, that inductance profile is positive slope. Okay, so based on the this equation, so it is clearly we can understand that for this positive dl by d theta, the slope of this inductance with respect to the rotor position. The change in rotor position. So that makes So under that condition, so the motoring operation can be achieved. Whereas the slope is negative, then so that goes to the generating mode of operation. Okay, yeah. So then this is about so operation of this mode, the motoring mode and generating mode of SR machine. And when it comes to the control strategies, especially as I mentioned, so that is depending on this the back EMF developed in the machine winding in particular, because at the low speed, because the back EMF is changing with respect to the speed of the machine, right? So therefore, here these control strategies in this, the current impressed are depend on the phase voltage and rotor shaft speed and phase commutation. And these based on this current waveform, the control strategies can be classified as low speed operation and high speed operation. Low speed operation and high speed operation. Okay. What is low speed operation? Higher, huh? Okay. Okay then, so actually here these control strategies can be derived based on the your speed of operation of the machine, means under low speed and high speed operation. So what is under low speed operation? Under low speed operation, the back EMF developed is of very small, right? So therefore the current go to high values, and therefore we consider to be like a chopping mode. So we prefer this chopping mode control. So under low speed operation, okay. And what kind of chopping mode operation means? See here we can also have a hysteresis band control or this frequency fixed frequency PWM control. So these are the two control schemes under chopping mode can be realized, can be used for this low speed operation, whereas for high speed operation, as the motor picks up the higher speed, under higher speed of operation, so the back EMF obviously it's increase. So therefore, so then the torque can only be controlled by varying the turn on and turn off angles of the rotor position. So, okay, so therefore under this high speed operation of the machine, so we go for the angle control mode. Okay, so this is how say we need to understand about this further with respect to the lower speed range and higher speed range. Okay, so to devise the appropriate controller. Okay, but this is the basic control strategy phenomena, but otherwise there could be various other advanced control mechanism we can do device. So depending on the application also. So where in which so we have designed this control scheme for this direct PB fed SRM drive. So where in which so we used like a variable DC based PWM scheme. Okay, like that. So depending on the some different type of applications, okay, we can also devise some okay the various control schemes as appropriate. Okay, yeah. So I think I will stop at this point. So from here onwards, of course, more on this. Okay, these are the various control schemes here. But here in the various control schemes, there could be like a different say merits and demerits also we need to see. But for that matter, one thing see for this there is a one single pulse scheme for this high speed also. This in this control scheme, see the changeover of this pulse. Okay, positive voltage to the negative voltage. It is like a sudden change in from positive to negative. So this is not an advantage factor, but this is a disadvantage rather. Okay. So, but see in other two cases, if we can see, so that the changeover from this positive to the negative is not okay immediate. So, but that can that leads to a kind of a some we call it as like a soft switching mechanism. Okay, but this is okay. So that is how it is. So now more on this control aspect. Of course, now see my. Of course, he is our academic colleague now. But he was my past research scholar in this area of work. So now I think he is already joined and he is waiting online. So in fact, as I mentioned, have other meeting and other class also. Regular class, so I need to take a leave here. So therefore, so thank you for your patience listening. And if you have any specific clarifications, of course. Anyway, so our continued my next speaker. Okay, so he will clarify. Okay, yeah. So thank you all.
here for solar module, which is working on electric vehicles student major project. It is based solar based electric vehicles. They are working on that. I'm also co-coordinator for Center of Excellence e-mobility at MIT Park. That's brief about me. And I hope that sir has already started the session on switcher reluctance machine. And I try to brief a couple of things which are necessary for me for modeling and control of SRM. Then a little bit on SRM advantages and potential in EV. So we will see that, and as well as we will continue with doing some model exercise. Also, we will try to do some model to understand it more. So basically, we will try to understand the principle of control strategy in reluctance motor, and that's what we will try to do. Now, switcher reluctance machine, we'll see a brief on control construction picture. Quickly I'll go through that because already points should be covered. So I try to look to which is necessary for me. So as we all know, reluctance motor work on principle of coil and silicon steel. So we have three combination of motors can be classified into these three categories. It can be with a coil or coil magnet and coil steel. So coil, we know when your induction motors works on principle of induction principle, the induced EMF is going to contribute for the motion. And in case of permanent magnets, we know that permanent magnets will contribute to the motion with the coil. And the other possibility of this having coil and a piece of iron. So when we excite the coil, the iron tends to move. So this principle is called a reluctance principle. So as we know very well, as I have already discussed, due to larger air gap is larger. You have when it's unaligned position, you have a larger air gap that results to a larger high reluctance. So high reluctance is high at this point. And when we exit this space, the rotor tends to move, and we have a smaller air gap, results into smaller reluctance or low reluctance. So this tendency of moving from high reluctance to low reluctance path is called as reluctance torque. And we know very well there is no coil on it, there is no magnet on it. This has been already discussed. Now I want to look at this aspect of reluctance. When there is high reluctance, okay, so we need magnetic saturation will be linear, whereas when it's low reluctance, we have more fringing or effect, or saturation is very high. So this is why I'm not covering that much part in detail. And in this key aspect is that for variable speed drive, we can see that it is very good to see that reluctance motors are more promising. And we know very well EVs are EV themselves are variable speed drives, and even water proofing application is also variable speed drive. So that's the reason in this aspect it stands very good. That's called some flat power efficiency. Possibly we will see somewhere some results are regarding to that one. Flat power efficiency in the sense you have more, for more speed range you should have more high efficiency. So this is omega, this is efficiency, this is flat power efficiency. Induction motors have the problem of low efficiency. In the sense when speed is low, efficiency falls down. And for permanent magnets it's intermediate. Though they are good in peak efficiency is high permanent magnet, but they are not for over the speed range, they are not contributing into the efficiency. So that's the reason it has a very good potential, and people are looking for switcher reluctance motor types in this case. A couple of other advantages. For our instance, as I told you, when it is unaligned position, due to reluctance, the inductance will be low. You can see the slope will be linear, and the slope of this one indicates the inductance value, and it will be low. And that's the reason you can see at unaligned position, low inductance value. And as it moves to saturation, when it reaches to this position, you have saturated inductance, that is aligned inductance value, and that aligned inductance value will be high. And as it moves from this side to this side, we have again the falling of this one. So this is very essential part to learn because it will help us to control. Yes, sir. Okay. So very essential part. So I want to highlight on this. So this is very brief about them, though it might be covered, but for us it is very essential to look into this. Now, when it comes to the governing equation, any magnetic circuit or magnetic coil, we have voltage is equal to R into I d psi by dt, where d psi this is the flux component, okay, in the rotor. So if we rearrange for this equation, the flux will be V minus IR into dt. So this becomes very crucial thing in our thing. Now, why we are looking into this one is that though in our previous slide, what we have seen is that so underlying inductance and aligned inductance, we can see rise of the thing. And most of the magnetics properties, if you don't consider this saturation, will give you inaccuracies. So if you don't consider, most models, what happens is that they will try to put all the lines in a linear way. So they is called as linear models. Now, linear models have the problem of inaccuracies. In order to sort out this linear modeling, so we have to consider non-linear characteristics of this. Non-linear characteristics. And we can see, if you consider the saturated profile, then it will be a non-linear characteristics, and because of that one, you have high accurate model. See? So that's the reason going into this flux is very, very essential. And if you consider only linear model, flux is equal to L into I, okay? And that's the reason we have voltage equation V is equal to R into I plus d psi by dt. If you put that linear into the characteristics, generally we know voltage equation can be written I into R plus L di by dt. Now, because L di by dt is only considered good and accurate only when it is a linear characteristics. But when it is non-linear characteristics, instead of considering this linear relation, we have to consider only flux. So the actual equation becomes V is equal to R into I plus d psi by dt. Now getting this flux is very important for us. And that's the reason if you arrange flux is equal to rearrange this equation, and if you rearrange that equation, you can d psi by dt becomes V minus I into R. Okay? And if you consider that one, if you put integration to both sides, then final equation will become this. Flux is equal to integration of V minus I into R dt. So this will help us to go inside accurately to get into the flux. Okay? And from flux, the co-energy is computed, and the co-energy from co-energy principle we can compute the torque is what, and torque equation. So is given by I square by 2 dl by dt. Now the other way of putting it is that since flux is not a linear, it's a non-linear characteristic. That's the reason we have N into I, and derivatives of that one will result finally. We can see that this is the energy stored, derivative of the energy stored in the inductor, and the power that is going to the shaft. So when it's going to the mechanical power is this one. So finally this into this. This is torque into omega is the power that is going to the shaft. So this is mechanical output. So this equation, when we correlate this one, again the equation will be same, that is I square by 2 dl by dt. Now to the beginners or any other one who are new to this line or anything, if you understand this equation, it is very essential. It is sufficient information for us to understand the control strategy. Now I square by 2 we will discuss in detail, and that's the reason we are working on dl by dt. So we need this inductance slope for the control strategies to understand. Now proceed on to that you can see it here. Now let's learn to this equation itself. And what we can see is that if you want to have positive torque, okay, the only means that it is independent on the current. For example, if I change the direction of the current, since it's minus I square, it results again to I square. So this I will not contribute, I is not at all contributing to the sign. Okay, so if you want positive torque. Now, whereas the sign is dependent on the slope of dl by dt term. Okay, and if you want positive t, that means you need to have positive dl by dt term. And this is nothing but the slope of inductance. Okay, and we have seen that from unaligned position to aligned position, the slope is rising. So here in this region, slope is positive dl by dt term. And if you want negative torque, the only means in this equation that is you have to continue to do written dl by dt minus dl by dt, which is nothing but slope is decreasing. So this is minus dl by dt region. So this positive torque, below variable positive torque means it is nothing but motoring mode. Okay. And the negative torque is nothing but typically generating. I hope this information is very simplified way to understand principle. In a way that you want to have motor mode, you want to accelerate in motor mode, all you have to do is that you have to switch on the phases when there's positive slope of inductance. In this region, we need to turn on. So I'm just turning on in this region the coil. When we excite in this positive slope of inductance, then we'll get motoring. The same thing when we switch on to negative slope region, okay, then we will get into generating mode. So this is very essential, switching from positive slope to negative slope. And let us take a case of 8 by 6 SRI. So where 8 is stated poles and 6 is rotor poles. And with that, what happens is that if you have 360 degrees total angle and the slope of the positive to negative slope of dl by d theta, when it comes to be divided by the rotor phase comes to be 60 degrees. So this 60 degrees indicates entire one cycle of that pole. So what we can see as we go back. So this position, if you consider nominative or if you take it as 0 degree, that means this entire degrees span is 60 degrees. And within the 60 from 0 to 30 degree, it will be positive dl by d theta, and from 30 to 60 degree, it will be minus dl by d theta. Okay. Now, if you want to have motoring mode, all you have to turn on or excite the phase in this region. So when the rotor is in this region, okay, in this region, positive slope of inductance, then you excite the phase. So that will give you the motoring mode. And the same thing if you switch on, excite the phase or excite the phase and tap the generating mode of energy. So there, what we have to switch on between minus dl by d theta position. So between these positions. So this is the way switching has to be carried out. Now we understood that positive and negative sign of this this one is on dl by d theta, where we switch on, where we switch off. Now, other important point that you have to learn for any application is that what is the magnitude of this torque, how I can increase or decrease. So the means that we can do here is that it is not depending on dl by d theta, but we can see the magnitude is dependent on I square. Okay. So the magnitude of the torque is dependent on current. So since it is I square, for example, in this case you just double the current, you will get 4 times the rated torque. So if this I is rated and we have rated torque on that, okay, so if you double the rated current, then we have typically, from this equation we can see we can have 4 times rated torque. This is really one of the essential part of reluctance principles. So if this is the current, and if I turning on and turn off with a positive slope, that means I am motoring in this region, and the magnitude of this one, the magnitude of the current will decide the torque magnitude. Okay. So these 3 parameters are very, very crucial points to learn. Is that when I am turning on and when I am turning off, and which region I am turning on and turning off, and also the magnitude of current. Okay. Now, the good point about the reluctance motors is that since it starts proportional to square of the current, okay, this is very good for starting acceleration, where you want to have higher torque. With a small minimal change in current or doubling the current, you can have 4 times the rated torque. That's what you can see. Which was in older versions of the electric motors. In the older versions of the electric motor, the older motor that was contributing to this one was a series motor, DC series motor. So DC series motor was also proportional to square of the current. The challenge in DC series motor was, though it was giving 4 times rated torque because of the current doubling, though it's the same equation related to that torque is proportional to square of the current, but the challenges that we face in DC is that we have effects of brushes and sparks and maintenance issues. Okay. So because of all these things, the DC motors, series motors were very challenging, and that was old, and nowadays nobody are using DC series motor. But in the current trend of motors, which can contribute to this torque is proportional to square motor, you can see here clearly, reluctance motor will help us. And the counterfeit of this one is that in this case, reluctance motor are producing 4 times rated torque, but I think so since it's a laminated steel core within the one, so easily you can get into current to X square R, and there is no problem with the brushes, and there is no challenge of sparks and all that, no maintenance issue. So that means it's the same property of the series motor which we can get in a better way in reluctance motor. So this is another key factor which is being currently used for in EV applications and everything also. So in a nutshell, if at all we can consider the magnitude of the torque is related to the current magnitude, the magnitude of the current, and the sign of the torque, positive or negative, is dependent on dl by d theta. So if we understand this base principle, I think so we can understand the basic control strategy of reluctance motors. So we'll try to learn one by one parameters and try to consolidate that. So these are the 3 parameters which are essential to control the reluctance motor drives. Now when it comes to control, okay, so there is a 2 way of understanding the principle here. So I want to look into this characteristic itself again. We can see it is that when the inductance is low, okay, and a basic inductance equation, the voltage equation of any inductor is that L dI by dt. Okay. So what happens when inductance is low? It's a low inductance. Okay. And when you have low inductance and when we have a full voltage applied to the coil. Okay. So when we have full voltage applied to the coil, full voltage of VDC, higher voltage of VDC. So full DC voltage, DC is converted to topology method. When we apply high voltage to that one, what happens is that because of high voltage and low inductance value, what we can see is that rise of current will be very high. And any motor equation we know very well. VDC applied is equal to R into I plus L di by dt or any back EMF component. Now back EMF component we know very well, this is dependent on speed. Okay. Now when the motor is at start, when the motor is at very low speed region, so when we say low speed region, okay, at low speed region what happens is that back EMF will be very low or negligible. So there won't be back EMF in low speed. So when there is no back EMF in this, and this is very small drop because the resistance is very small current. So at low speed what happens is that the applied DC is nothing but it becomes L di by dt. Okay, since back EMF is negligible, this is negligible at low speed. So we can consider applied DC, high DC voltage L di by dt. And that's the reason in low speed what we can see is that since at low speed, low inductance value, if you turn on the phase here, if you give high voltage DC, VDC applied here, okay, what happens is that the rise in the current di by dt will be very high at low speed. At low speed, when you switch on at low inductance value, so whenever you go in this region, you may get into very high di by dt that will go to very high currents at low speed. Okay. Now at low speed, the best way control strategy is that we will, though it is going to very high current, we will try to limit the current. So this limiting current strategy is at low speed. Okay, so when the motor is in low speed, it is preferred that because of high DC voltage, high voltage DC, it will go to very high current because of low back EMF. So we have to limit that current through the hysteresis. That's the reason at low speed you have hysteresis control. So since this current will rise to very high value, we will limit the current to I reference. Now as I told you, I reference T on, T off will help us to understand and get the torque. Now when it is 3 rated, so we have to maintain that I rated reference. So we will put the hysteresis control, and one of the control strategies is hysteresis control, we put the band control. So we will put that controller within this period of positive torque. And during demagnetizing, we will see in converter that when you turn off, the demagnetizing region itself is giving the negative voltage to it. So we don't have controllability here. So we have only controllability of these 3 parameters, I reference, T on and T off. Now, as speed increases, what happens is that this back EMF, as speed increases, this back EMF is going to come into picture. Now, as speed increases, back EMF is going to increase. When back EMF increases, the actual equation becomes like VDC equal to, instead of now it becomes L di by dt plus back EMF in. Now, if you see that this back EMF will come this side, that means VDC minus back EMF is L di by dt. Okay. Now this, you can see it has reduced the voltage. Now what happens, as speed increases, since the voltage is reduced, that is V minus ADC. Now the same, and you can see that when this inductance comes down, so you have seen that because V minus EV by L, you can see this voltage is reduced. That means your di by dt will reduce. Okay. Now interestingly, as you go to higher speed region, okay, it will fall within the limit only. Because as speed is increasing, your current is actually sort of kept at maximum limit, okay, and because of back EMF effect, the current will fall. You can see it here. Now in high speed region, the only means that you can increase this area. Now remember always one thing, this entire area of I reference T on and T off, I reference will contribute to the torque. More this area, higher the area, higher the torque value. Right? Now what happens is that as speed increases, since this area is falling down, you won't get the required torque levels. What you have to do is that at that moment, at higher speed, it is better to push this T on control. So at higher speed, you can control this T on and make it that at higher only, you can get into more current, and more current will result into a more torque. So more area will result into more torque. Now in a nutshell, at low speed, it is better to have switching between hysteresis control because current will go to high value. At high speed, back EMF itself will go to the limit. That's the reason we can have control through T on, fixing T on. There are a couple of control strategies. The simplest control strategy is that in low speed, work with three parameters: I reference, T on, and T off. And in higher speed region, by varying I reference, and higher speed region we can control by T on to get more torque. So this is the simplest approach to understand minimum control strategy of linear reluctance motor. And we will try to see some cases of that on some simulations and understand the principle. So I hope that I'm not connected one-to-one in conversation due to some technical issue. But I wish that by now you have understood that what are the essential parameters to control the reluctance motor drive. And this is the overall control strategy. We can see here three parameters are essential for us. We need to get I reference, okay, and T on and T off. When it's low speed you work with I reference, T on and T off. And when it's high speed, it will work with T on and T off. Now we can see here a simplest output control, that is speed control. We will see the speed of the actual speed of the motor and reference speed. The error is processed to PID controller, and we know very well in basic rights is that the outer loop will decide the inner loop, that is torque reference required torque. Now this torque reference has to be converted into current reference, and we know very well this is quadratic relationship. As we know very well, torque is proportional to square of the current, and if you want current, it's nothing but root of torque. So if you have torque reference value, if you put the root symbol, then you get the current reference. And this reference and T on and T off will help to control. That's all. Okay. And at higher speed the torque reference, the required torque, and at higher speed we are mapping between what is the torque required. As I told you, T on should be controlled with reference to the torque. So we will map with the reference to torque and omega. So the lookup table for torque and omega can be made for T on angles, keeping T on either fixed or a variable also. So that's the reason in low at high speed what happens is that this will switch on to angle control. We are only controlling through T on and T off in higher speed. So we can see this is the torque reference coming, and I am taking the actual speed. And for this, what is the T on calculated value, estimated value? And this distribution comes from the analysis that we do on the prototype. So with this T1 and T off, we can control in higher speed region. And basically, other challenge in reluctance motor is that this is very essential part to learn that to control the motor. If I want to control T on and T off, that means I need the position information. So position information is very essential part in this case. That's the reason for a drive we need to have position information. That position information will help us to when to turn on, when to put the controller. Right? So this is a need for that one. Though a couple of control strategies have been already been built. Okay? The basic controller is requires positions itself. Nowadays we have sensorless controls also. Okay. Now, basic system of a reluctance motor will have this position information and when to turn on, with what should be the current reference. This is what we can learn in the control of reluctance motor drive. Now, when it comes to topology, we know whether to switch where to place topology. What happens is that I just want to bring to this, though it might be covered there. So when S1 and S2 are on, this is classical topology, the VDC is applied to the coil. Okay? And there is a mode that when S1 is off, only when S2 is on. So that means it will free, the energy stored in this one will free you through this. Okay? This is when positive VDC 0, positive VDC 0 applied. Okay? Now, this is for soft switching. What is meant by hard switching is that, so when both are on and both are off. Okay, when both are on, it is positive VDC, minus VDC, positive VDC, minus VDC, positive VDC, minus VDC. So this is called hard swapping, this is called soft swapping. Okay. Now, the other part is that once the switching pattern is over, after switching is over, in that one, when both the switches are off, when both the switches are off, this is off, this is off. Now what happens, the energy stored in the inductor will free wheel through the diodes. Okay? So this concept of freewheeling is called demagnetizing. Right? So this component is actually controlled by the system itself, by the inductor itself. We don't have during this period any control over S1 and S2. So we can see it here. This is what we can see. This is what we are turning on and turning off. This is our control part, T on and T off, when to on, when to off. Now, when after off, right? After off, the demagnetism, the minus VDC is applied by the system, okay, through D1 and D2. Okay, so this is a demagnetizing component. Now, this actually helps us in saving energy also. So this is a regenerative component. So what is the thing is that we can see it here is that, so during regeneration, this energy is given back to the source. So demagnetic component saves little energy back to the source, and from source we are getting energy, and this capacity will help us to energy buffer between the source as well as the coils. And basically the other topology is alternate topology, single switch per phase, we are exciting with demagnetizing done by other phase, other switching. So that's our brief over there. So most widely used is classical single two switch per phase topology. Okay, I hope that you understand now. Only thing that if power circuit is same, the significance comes with the switching, when to switch on, when to switch off. So when I am able to switch on and switch off, if I know the position and switch on and switch off, that will be sufficient for me to control the servo. Okay. missed out that one. I'll try to skip up that one. So that's about the basic control of reluctance motor. And for essential part of that one, as I told you, we should have the knowledge of flux linkage characteristics. That's what we will see again, how to do it. Okay. So I hope that the basic of the control aspects of reluctance motor is been understood clearly. And we'll see now, we'll try to model the system and then we'll look at that. Any questions till this part? The audience, on your audience, you can put it in chat also. Somebody can put
How to decide the turn on and turn off angles numbers?
If no questions, we can go further. So I hope that there's no questions. I'll try to just go to.
Any more questions?
Now, let's try to learn about modeling of reluctance motor. The first point that we try to learn is significance of the flux linkage characteristics and how to get these characteristics, how do we determine the characteristics, in what ways we can determine the characteristics, and then how do we compute static torque characteristics out of it and MATLAB simulated model, and try to see some result that has been already there. So this was okay.
We'll see that.
Vijay sir.
The first thing very important for us to learn that we begin at the point of we should.
Idealization of flux linkage characteristics will give us model the performance with cannot predict the model with accuracy. Okay. So this is the essential part to have flux linkage, and linearization or idealization of that one is cannot predict the performance of that one with something like this. So the model, there are a couple of models authors have worked with the linear models and everything, but they won't be that much accurate or relevant kind of system. Whereas when we consider non-linearity of the flux linkage, it is very good modeling, it will have more accurate, but complexity modeling is that because of the non-linear flux linkage characteristics. And it is very difficult to get it a mathematical relationship between them. So, a couple of the ways in motor drives to get the flux linkage characteristics of any motors are one of the methods is using finite element method tools, okay, like any tools like ANSYS or JMAC or electromagnetic tools. So, EM tools will help us to get the flux. And the real challenge of this method is that finding the characteristic is that you should know all the dimensions of the motor. All the dimensions, materials, properties. All that you have to learn. But these are very good at the stage of before designing a motor. So they will help to design a new motor, new topology. So by designing this will help you to optimize to get into that one and finally come up with the design. When you have already a motor that has been already procured, already been there, the way to get the flux linkage characteristics is that through an experimental approach. Right? This works good when you have a motor. Okay. So in either the way, if you have a motor, all the dimensions, materials or nothing, you can get the flux linkage characteristics through the tools. Okay. And if you have a motor and if you don't use any electromagnetic tools, the other approach that you can do is that using experimental approach, that is direct measurement approach. And 1 minute, let's start.
Guys, 15 minutes break.
I think so. Mr. Kumar will inform you about the play. After that, I think so we will start back. First 11.
So, how to decide the rotation angle? Tan in and tan off angle. Turn on and off.
I'm audible?
Yes, sir.
So, turn on and turn off, identify that one. We will come to that one because that's part of that one. We will be addressing that issue. So, I think we will follow. Now, that point we'll discuss. Can we follow? Is that fine? So, turn on and turn off angle depends on the torque, ripple requirement and everything, where the torque has to be, based on the torque ripple, where it is high, where it is low. Selection will be based on that principle. That also we try to address it and see. Okay. I'll show you one example. Fine?
Yes, sir. One more question. What motor you're using? Rating of the motor.
Yeah. There are a couple of models that we have worked. I worked with initially when I was doing my master's, I had with 4 kilowatt motor. That's all been right. And in NIFD bundle, I have worked on 2.2 kilowatt motor. And then now in my lab, I have on standard bracket and so on.
What is the rated speed?
Huh?
What is the rated speed?
The rated speed. The rated speed of 2.2 kilowatt motor is 1500 RPM. I was working in NIFD. Then the 4 kilowatt motor was rated with 2.2 kilowatt motor was rated with 3000 RPM. Then 4 kilowatt motor was rated with 1500 RPM. I think so there's a small power motor, which is typically high speed motor that currently we are working with 5000 RPM.
Okay, sir.
So can you go more than that? Can you operate the motor for the speed or range of speeds? What is the range of speed?
Sir, what is the minimum range and maximum range we can operate?
Minimum range and maximum range of any, for example, it's a 4 kilowatt motor or we had a 2.2 kilowatt motor, which was rated to 15.5 kV. And typically we can go ahead till the 6 times of the rated packet. That is 1500 into 6. Typically tax value we can go with graphics focus. 5 to 6 times of the rated speed we can go with the motor.
So just 1 second, sir.
One more question. Yes. Yes, actually, Vijay Bhaskar, myself, faculty from associate professor, associate professor from NIT Rourkela. And so, nice to meet you. And so, your explanation is very nice. Actually, my question is that you are using the PID controller, right? So, in general, we will use that PI controller for maybe like for induction motor, for any of the motor applications. So, okay.
Because basically drives, most of the drives are susceptible, control is done by PI.
Okay.
D is little bit sensitive to the noise.
Nice, yes.
Only when there is no transients, most of when there is no transient applications, we should have to choose D also to minimize overshoot.
So as you are using that like SRM motor, so due to some noise, you are included that, I think so, that D controller, right? Differential.
We are not used to DA.
Okay.
We are most PI only.
Okay.
To one extent, because they needed to minimize overshoot.
Okay.
To minimize overshoot, we use D.
And then sensors for sensing of for the all sensors only. Okay. 3 sensors you are using for that, right?
For SRM 8x6 motor,
Okay,
6 motor. We have used for the 4 sensors within that motor.
Okay. For each space you are using for one, I think so. That way you have been used.
No, even actually that depends on the sensor mechanism control strategy.
Okay.
Before these 4 sensors, if you have more number of pulses, you get more intimate accurate positions you get.
Okay.
If you have more intimate accurate positions, that will help you to accurately get the speed value.
Okay.
And if you have even 2 sensors also, it's possible to have 4 combinations. On, off, on, off. So 2 typically 4 we get. But if you have more 16 samples between 60 degrees, you will get more accurate positions to identify actual happenings. Or else, what happens is that intermediate state, you have to just assume that you have to just integrate and you have to get a position of the street. So that's little less accurate, but it's possible still.
Okay.
So interestingly, even if you have one half sensor also, you can work. I have made it work.
Okay.
It's just one half sensor is enough, one information is enough for me to identify entire position.
Okay.
Every lights I am identified. So accurately, how accurately you get in between is up to you.
Okay.
So logic is a logic driven. 4 sensors, if you use 16 logics, we get 0, 1, 0, 1, 1, 0, 1, 0, 16 combinations. 16 combinations will give you 60 degrees. So you have more intimate accurate position information.
Okay.
And type of sensors, if you use encoder, we know very well. But encoder will give 104 pulses within the entire span. So that is more accurate.
Okay, thank you.
After the values, we know.
Okay.
The algorithms can be built, sir.
Okay, fine. Thank you, sir. You can proceed.
Yeah.
One more question. Hello?
Vijay sir, one more question.
Yeah.
I am Prashant Patel, sir. So I am also working on same SRM there, sir. So you suggested we need to turn on switch before the actual position. So if rotor Sir, hello sir. Am I audible, sir? Sir, to overcome one issue, so we need to turn on switch before the actual position. Actually, you suggested, sir. Yes, sir. Yes, sir. Suppose if rotor polar and stator polar are same, So no gap between the increasing induction profile, increasing induction profile and decreasing inductance profile, sir. If we start before, so that is maybe generating mode. So it will produce this negative torque. So maybe average torque will be decreases. Is it correct, sir? Yes. So is it suggestible for that? In that case, is it suggestible, sir?
I'm trying to put my PPT. And share. Sir, Krupakar, you are not able to share the screen. Present. Is my screen visible, sir? Yeah, now it makes it some time. Sir, you're talking about
Inductance profile, sir.
this is not.
No, yes, sir, this one. But go to first before slide, sir. So actually, so increasing inductance and decreasing inductance both are start at one position. If we start, if we give the switching pulse before the actual position, so maybe that will enter into the generating mode. Is it true, sir?
Slightly generating mode.
Generating mode means negative. It will produce negative torque. So average torque maybe decreases. It will decreases maybe.
This region, couple of degrees from this side or couple of degrees from this side, okay, will help us is almost similar length. We don't have much change happening in that way. So when you go to higher ratings and everything, if you switch on in this region, okay, it's still not having that much torque, but this additional torque is going to help us to produce more torque. Though we have to put on exactly switching, look to proper way of what we call it as how much negative torque is going to come. This happens, but you have to choose in such a way that angle that you have to help out that you have to produce positive torque and more for torque production has to be done. Typically, you can go till -5 degrees.
If beta R is greater than beta S, so is it suggestible? So it is suggestible. But if beta R and beta S both are arcs are equal, stator pole arc and rotor pole arc are equal, so no gaps are actually both. Yes, sir. So in that case, it will produce negative torque.
Yeah. In that case, it will produce negative torque, but by the time what happens is we might have already attained, in that case, we might have attained it is only essential when we go beyond the rated. So there is something called as flat top region of the curve. So where back EMF is actually equal to VDs. So nearly equal to VDs. So during this point we have flat top of the curve of current. Okay. Now, beyond this, when you are going, we need to have more excitation angle to advance angle for control strategy. In your case, I think so when rotor poles, stator poles are same, I think you don't get much noise. But we have to see that till what point you will get this flat top curve and what point you will get the rated top. So that's only we have to switch on, we have to see that. So see to that angle. Very good. So only it happens is that when we have rotor pole and stator pole in the same grid, then you don't have much scope to control strategy.
Yes, sir.
Or you have to push T off also.
Yes, sir. Yes.
So T off can also be adjusted along with that such that you have more area. So, but only thing that contributes is that T off is pushing towards this region, you have more ripples. If ripples are compromised, I think so down the line, you can push it more where you don't have scope here. You can push it into right.
Okay, sir. Thank you.
And are you asking about this also generating mode? Why am I putting it here? Is that question also? No. So this also actually what happens is that no generator will work without excitation. So we have to get excitation as a generator also. Generator needs a magnetic excitation. So this small region, before you move to generating mode, it will be opposite curve. So this is the excitation, and you have more current in generating. Through this waveform, there you will understand that small excitation is actually required because you cannot have self-generation. That's also techniques are there. your magnets and everything that can help you in generation. But without magnet, you have to provide a small magnetic path for excitation to get into generating. That's the reason a small region of excitation is required for this certificate. So I think just a couple of people may have questions.
Yes, sir. Okay, sir. Thank you, sir. Thank you, sir.
Fine.
Yes, sir.
Sir, one more question. Sir, regenerative mode of operation. Can you explain?
Regenerative?
Mode of operation.
Regenerative mode of operation this way that wherever you are give the excitation for a small duration and that get more correct. Maybe I show the generator waveform that I think so we will get an idea. Okay, here you can see that we use we can see that this is the motor mode. Now when I am switching in the positive region, I am getting the positive current, and we can get the positive torque. And this is what you can see. This is a magnetizing component and this is a demagnetizing component. Right? Now we're getting positive torque. The next part you can see here is a part of generation. This is the LPV generation, this is LPV mode. Now in opposite, what happens is that if this curve remains opposite, that means you have excitation this side, generating mode this side. So for a generator, you can see I'm switching in this direction. So I'm switching here, and when I'm switching in this direction, this part is your excitation required for the coil. Okay, now always remember that one challenge that we get is that in a generating mode, any generator, the question that comes is that how do I achieve this excitation? So because definitely there has to be some magnetic field, because if there is no magnet that can be rotated or there is no magnet, obviously that cannot produce the generation. Generation cannot be happen without excitation. Either it can be excited through coils. Okay. The other means people use is that magnets for a generator. In case of magnets, there is no challenge, no issue because magnets will be moving that will create cut the coil will induce EMF that will produce energy. So that will act like a generator. But in case of generators without the magnets, okay, the only way that we have to give is that we have to create that electromagnet at the base. Excitation requirement is there. So what we are doing in this feature is that we are exciting the base and we are creating that magnet. Within that magnetic field, if rotor is moving with mechanical energy within that one, that will be generated. So this region. So this region is actually a generating region. So this will give you more. You can see the area is more, the excitation is less. So excitation is less and the area of this one is more, indicates that you are producing more energy than excitation. Right. Now, couple of my part of thesis work when I was working with a generator for wind energy conversion system is that how do I get this excitation? So this piece is also called as self-excitation method. Okay, and there's something also called as initial excitation. So at the start, how do you get initial excitation? Either through capacitor which is already stored or through some magnetic energy. There are different methods of excitation of initial excitation. Now, part of my work was that if we use solar energy, nearby solar energy, that also helped me for the initial excitation that we keep into generating mode. So, and this configuration changes based on type of processor. Is this question clear?
Okay, sir. Thank you, sir.
Okay, so we may run stop with calculation. Good. So now we have reached to find. for reluctance motor. And this is a three-dimensional view. Now, flux is a function of current and position. That's what we have seen. It's a function of flux is a function of current and different positions. Okay. Now, in three-dimensional view, it will look like this characteristics. Now, the static torque characteristics also over the positive and negative character. Now, understand that if after 30 degrees, from 30 to 60 degrees, it is actually negative torque of the same. It's the same characteristics, but in a negative way. So we can rebuild if you have 0 to 30 degrees developed, that is sufficient to build the negative values from 30 to 60 degrees. So that is the negative torque region. So overall, basic block diagram of any simulation model of reluctance motor requires the flux linkage characteristic, that is current characteristic. Current is actually a function of flux and position theta. So this information, and then torque is function of current and theta. Okay. So we need to build these two information more accurately into the model. So after that, if you know the flux, this is the flux. This is nothing but a voltage equation. You can see it voltage equation. So flux is nothing but integration of V minus flux is integration of V minus I into R. So V minus IR, I is coming, V minus IR is integration, you are getting flux. Now flux is an input and then theta is another input, you are getting current. So this characteristics is essential. Now once you get the current, you know position and current. For the position and current, you will get the torque. And 0 to 30 degrees if you do, you will get positive torque. And 30 to 60 degrees, you will get negative torque. And as far as this is the mechanical equation, this is electrical voltage equation. Any motors can be classified into, the models can be classified into voltage and torque equation or mechanical equation. So you can look to that one. This is the current characteristics, and it will be again from 0 to 60 degree. We have three-dimensional view. So this is also torque characteristics, function of current and theta. Now, if these two data are available or we build, so this data can be built using even FEM models, okay, modeling technique, or as I told you, experimental approach. In both ways, we can build this model, and this is essential for us to have accurate control of the motor. So once we build, we can clearly see that V minus I are being integrated, and we are building that lookup table here, and this is lookup table approach. And there are mathematical approaches where we can also put this flux as a relation of current and theta in terms of mathematical equations also. So during my master's, I think so my paper, one of the paper on switch related generator has that equation based modeling. So where flux can be equation and current can be computed with the current estimate can be done. So mathematically also we can build. Even torque equation can also be mathematically represented. So approximations have already been built. There are so many models built in. Now, one of the approaches, very fundamental approach is that if you have the data, I think so it is put up in a lookup table, then use that. So this is a resultant torque. This is a mechanical equation that we can build. As I told you, this is the motoring mode. So this requires position information, very important. Unlike other motors, even in permanent magnet-based motors, we have position sensor requirement on it. So here also we require position. Based on the position, we need to switch on and switch off the voltage, giving the voltage to this one. This is the excitation, and based on which position I am going to give the excitation. It's the essential part in reluctance motor. Now we have sensorless controls also very well established for reluctance motors. So motoring mode, positive torque. negative torque, we will have generating mode with a positive moment. Another point that we have to learn with the little bit advanced control strategy, or I'm just letting out my thesis work, the part of the work that we had worked in NIFD Warangal is that the one of the learning curve is that the excitation, when we see this excitation of the coil, we can see the excitation DC voltage. When the DC voltage is very high, and we are switching on, and because I already told you, when DC voltage is high, current will go high. We need to put on switch on and switch off. That's what we have seen, that hysteresis control has to be limiting the current. Since the DC voltage was full high, so that's the reason we require hysteresis control in low speed region. So when this fixed DC voltage, which is high, so which will current will rise in a very high value. We need to limit the current using limiter. Okay, and because we know whether it's vacuum will be low and low speed, we need to have a fixed DC voltage which is high. It will produce very high, and that's the reason we need HCM control, hysteresis control mode. And this need current sensors, because we have to sense the current, then we have to limit the current. So this needs sensors and it needs current limiters. So current limiters also required. And also conditioning circuits are required, because sometimes what happens, because of hysteresis, the bandwidth, if you close less this bandwidth, you have higher frequency. So higher frequency may not be possible to switch on the IGBTs required in the circuit and everything. So we have to put limiters for that one, less than 10 kilohertz switching mechanism. We have to limit that one, and those are also required when we put on to high voltage DC hysteresis control. The other way approach is that interesting approach that we can identify from Panda sir's thesis. Panda sir has done in IIC Bangalore. They have done thesis on reluctant motor. Based on their work only, I started to work and develop that one. So one of the work suggested that interesting work is that, what if this voltage is decreased? What if the voltage is limited? At the initial one, if I minimize this voltage, what will happen? So we know very well VDC is equal to VDC minus back EMF equal to LDI. This is what equation we have seen. At low speed, this will be very low or typically zero, right? And at low speed, because of that, this is very high value. That's the reason we are getting high DI/dt. Okay. The interesting point that was thought is that, what at low speed if I also reduce the voltage NC? So if I may reduce this voltage in low speed if I reduce the voltage, what happens is that my equation becomes VDC, which is low, okay, becomes LDI by DI by dt also reduces. That instead of going into very high, the slope of that one will fall very low. Again, it might be a chance that it may come into angle control only, fall in that limit. So in that way, what happens using variable DC control strategies, it will make you to enter into single pulse mode by varying VDC with reference to the speed. So if you vary VDC with reference to speed parallelly or linearly to one extent, we can get that it will always work in single pulse. So that was the idea of Parnassus thesis, the variable DC. The advantage of that one, what will be that one? You need not check for currents. So current sensors or currents, their sensors, you don't require. So it will eliminate these sensors. And after that, also since it's not giving hysteresis control, even limiters are not required. Okay, because they are working, this is at higher frequency, whereas single pulse mode is low frequency. So obviously, even the condition circuits required for that one, all that thing will be reduced in case of if you create a variable DC instead of fixed DC. Okay, that's the key role or the key aspect to understand the elimination of hysteresis control. Now that's called variable DC control strategy. Now with variable DC control strategy, if you vary with reference to speed, so with the reference you can say this is the fixed DC. If you vary linearly with reference to speed, okay, it can eliminate need of sensors, limiters, and conditions. So that's a interesting point that we can learn. So variable or reduced voltage during commutation will also help us in another important point. So this is what we have to stress here. Now, hysteresis control has another drawback is that if you have a loop of that one, there is a possibility of having plus VDC to minus VDC, plus VDC to minus VDC. The rise or the fall of the current, the di by dt in this case, will be very high. And high di by dt will result into more vibrations, noise, all that thing will come into picture. So higher this DC link. Now, to minimize the noise, interestingly, this in variable DC control strategy, if you have a fixed DC control strategy with angle control mode, even you have positive VDC to negative VDC. So we have this 2 VDC control. Whereas if you vary this voltage as proportional to the speed, at low speed, this VDC will be low. What happens is that because it's a low one, okay, this the lower version of plus VDC to minus VDC, low voltage, will have low di by dt, and this will result into low vibration, noise, all that. And vibration typically happens during this period of transient from first plus VDC to minus VDC, and that in fact we can see that if you reduce the voltage in simple way, naturally, if I put it, if you have variable voltage and you are during commutation, if you have variable voltage, obviously it will help us to reduce the noise and it will help us to eliminate the sensor. So that was the principle of variable DC control strategy. Now, the challenge of this one variable DC control strategy, fixed higher DC voltage is that irrespective of that one, there is still vibration. So there is still vibration in this control strategy. We cannot omit the vibration because you have to give commutation plus VDC minus. What if I introduce positive, negative, or positive, negative during that time? There might be a possibility that I can have a zero state also. So this zero state is not possible in this case. So if you give zero state plus VDC, 0 and minus VDC, this will minimize even noise. Okay. Now, the idea that we thought that we started to work with, started to explore is that to bring up a PWM control strategy by which we are eliminating hysteresis. There is no hysteresis PWM control strategy. We are working with the duty cycle. And there is a possibility of having zero state also, which is not possible in single pulse mode. By that, what happens is that we have lower noise and lower vibrations and everything, and also it will also we can see that since it's working on PWM technique, the current limiting or current the current limiter required, or we are just avoiding hysteresis, and hysteresis is because variable DC. So at low speed, what I do, I'll start with variable DC and the duty cycle. Sorry, duty cycle. So if I change the duty cycle, I can change the rise in the of everything, and but the variable DC will help us to eliminate hysteresis, and noise can be minimized with the zero potential that can happen. So this was the idea that we started to investigate, and we put this into water pumping application, and we started to do some small experimentation of prototyping and everything. So these are the three control strategies. We can see the simulated models of that one. Here you can see stresses control where we kept the band of 0.5 amp and we started to look with the control strategy. You can see that we are getting stress control and four phases will come in picture. So we have other three phases contributing. We try to see the waveform also for understanding. And this is single pulse control strategy. So since here VDC is high, we can see that there is no possibility of zero potential here. Whereas there is a potential of having zero positive and variable DC. We'll get variable DC which will eliminate haze stresses control also. So the motor was rated with 240 volt, and if I remember 240 volt DC. So we need not when it's not higher voltage. Okay, when we need to have high stresses control, and because we can lower the voltage, we can eliminate that one also. Now, all three parameters, three control strategies can be implemented. This is a practical waveform that we got. This was stress control and this angle control, single pulse mode. And this was PWM control strategy. For the same parameters, we started to test. This was simulated, this was started to test. Now, the investigation of this one, stresses control, single pulse control, PWM control was one of the parameters. I just want to briefly talk those part of the thesis for the water pumping application. But initial study we made between these three control strategies to know a couple of points. So that will help us to understand what exactly we are trying to do. So this was a practical setup that we had in NIFD Warangal. This was a reluctance motor. Now we were trying for pump load. So for pump load, we know very well it's a quadratic load. This was a very important point that we discuss again. So torque is proportional to square of the speed. Okay. So this is what you can see. The power for the loading for power is cubic of speed. So for this, we try to validate for this power curve and see that at different speed what would be that one. So we can see peak current. This is stress control. What we can see the diamond shape is nothing but stress control. This is stress control. We can see peak phase current. Okay, is low. Okay, typically we can see it around 2 amps to that one to maximum rated is on peak current here around 4 amps for the small load which started to test. Okay, now SPM single pulse mode, we can see single pulse mode, we have having higher peak current. Okay. So because they are here full VDC and fixed VDC, these three are in fixed VDC, these two are in variable DC. So full VDC in single pulse mode will give you a very high current. So peak current will be high. Okay. And as a result, we can see it clearly that peak current is very high. The next is even PWM technique with higher voltage DC, with a fixed DC voltage. If you have fixed DC voltage, you can see it is PWM technique is helping us in having lower peak current compared to even stresses control. And compared to single pulse mode, the variable DC peak current is very, very low. Okay, fixed DC, that is the black dot. Yeah, this is black dot. So next, what we have carried out is variable DC SPM technique. So variable DC SPM technique single pulse mode, where we can see it, peak current is actually lower in the lower case because they have reduced the voltage in lower speed. Okay. So because of that, we can see that it has lower and finally it reaches to its own condition, both remain same. Right? So that's the reason variable DC will help us to minimize even the peak currents in lower a single pulse mode. And finally, when we apply this variable DC along with the PWM control strategy, we can see it is helping us in low phase current. So peak current is low. So peak current gets low in this control strategy. And other performance parameters that we can investigate and see is that this is practically often one. Try to investigate that one is that even torque ripple is also very essential part. So we can say that ripple is in case of because the hysteresis work on ripple based hysteresis control and current control is very good in torque ripple minimizing, but it requires current sensors. SPM SPM with the fixed DC also at higher DC will help us to minimize the will have more torque ripple. Whereas when we see the variable DC PWM strategy is having lower torque ripple, lower the DC. So this will help us in terms of minimizing torque ripple, which further helps us in minimizing the ripple. So this was measured noise through the noise meter. We tested that one, and we can see that typically around more than 5 dB of reduction in noise, especially in low speed region. And even in high speed region, we can see from the control strategies from the SPM, as I told you, since it's positive VDC, negative VDC is going to come. Definitely, this is causing more higher noise compared to other strategies. Now, PWM also has a positive, negative, and zero possibility. That's the reason you can have lower noise with the zero possibilities. Whereas the variable DC, and as I told you, because reducing the voltage will help us in reducing noise. Also, we can see at lower speed, but as it goes to high speed, it's reaching with along with the fixed DC. Okay. And noise in terms of variable DC PWM technique, okay, it is actually completely reducing the noise, and it's contributing at least on 5 dB reduction in noise, 5 dB to 7 dB reduction. This is actually a very good level of reduction in techniques. And also efficiency also we tested to find the efficiency, and we can see that efficiency is also very good in variable DC PWM control strategy. And what would be the advantage of that one is that we are eliminating sensors from HCM control, and we are also eliminating the noise of this one. Noise is eliminated from that, and these advantages are reflecting this variable DC PWM control strategy. Because of variable DC, we are eliminating the sensors, the current sensors. Okay. And because of PWM control strategy, we are minimizing the noise. So with that, what we can say is that summary of variable DC PWM technique is that it will reduce the peak current also, and lesser torque ripple and lower noise and better efficiency. Also eliminates the current sensors and current conditioning circuits. This we have seen in a practical way. Is the point clear till this point? Anyone have any question on this? Have any question to ask, or we shall be move on? Okay. Yeah.
You have used the current right?
Yes, yes.
So my question is that as you are maybe operating for a different speeds or maybe a different operating conditions, so how you are fixing that current? That's what my question.
Yeah,
And
that will
dealing with the torque controller also.
yeah. Fixing current, the maximum current has to be fixed with the maximum rated current, rated torque of the van. So in your controller, if you see the controller, the torque reference will give you the current reference. The load and fundamental point in any motor drive system is that, always this is very very fundamental point to learn or to concentrate is that, okay, when you change VDC, when you vary the VDC, most of the motors in general, when you vary the VDC, you can change the speed of the motor. Okay? So when you vary the voltage, we can change the speed of the motor. If it's a DC motor, simple. DC voltage, if you vary, we can vary the speed of the motor. If it's AC motor, we are changing AC voltage and frequency both to get variable DC. variable speed. So this is for DC motors, this is for AC motors. This is basic principle. But the other part is very, very essential to learn is that it is not that if I change the current, I get the change in the load. This is totally the wrong principle. It is the load, if you put the load, then you draw the current. This is very important to understand. So it is the load that decides the thing. Or if I put in a single statement is that it is the load that draws power. Fine. So when there is a shaft, and if the shaft, if you put the load torque onto it, then only it will draw the current. Now here also you can see it here. The torque reference is deciding the current requirement. If there is no torque requirement, okay, if there is no torque requirement, obviously your reference will follow. So that means lower the load torque, lower the current reference. Okay. So we already have learned that one. T on, T off, and I reference. I reference decides the torque value. Okay. Now what is the load requirement? Then only you can put it to T reference. Now if you fix it to maximum value, maximum torque, as speed increases, what happens is this area is going to squeeze. When area is going to squeeze, the current will not rise to that mark, it will fall within as speed increases, because this is going to come down, area is going to come down. So by that what happens, torque also is going to fall. So current control, if you want to do based on the current, based on the torque, as per the torque, you have to map this I reference value.
So if you want to maybe going for above rated speed, I think current is again further
increase. No, above higher speed, at higher speed.
Yes.
At low speed, for typical EV application, what happens is that at low speed, we'll see this. At low speed, you need to have high torque. At low speed, you need to have high torque. This is the requirement. Okay. At that point, what are you going to do? You have to increase the current reference.
Yes.
When speed is low.
For above rated speed, like
above rated angle control.
So that maybe current should be taken, right? So that's okay, fine.
So yeah, another beautiful point about reference mode is that, which we can see that it is relevant to the EV application is that this is what we can see. We will try to see the simulation of that. So we look to that part enough. Any other thing? So we look to a little bit into EV, because I wanted to bring this point of reluctance motor by relevance for the EV application. So any vehicle characteristic, I quickly go through that one in a simple way. That's very essential to learn. Any vehicle characteristic require a constant power region. That means that the torque should fall as speed increases. So this is hyperbolic characteristic. This is actually ideal requirement of the vehicle. Now, practical requirement of any vehicle is that at low speed, this is a rated speed. Okay, at rated speed, you need to have high torque in max. Okay, and above that, it should be in constant power region where torque is falling. Okay? Constant torque and then falling of the torque, constant power region. So in IC engine, because engine characteristics there cannot match, that's the reason we need clear requirement. I'm not going in detail on that one. So whereas in electric motors, this is the beauty of the electric motor is that vehicle characteristics, which is practical characteristics, is directly mapped with electric EV. So EV's characteristics are already having this constant torque till the maximum speed. After the rated speed, till the maximum speed, this is the max vehicle speed. Okay, this region should be more. Okay, expected should be more. This should be low. That means as much as the low speed it should have higher torque. Now the SRR control strategy is that it is very suitable for this kind of applications. Okay, I'll just try to show that simulation. switch reluctance machine application already one of the applications is there. So more particular characteristics are required. If at all you have particular characteristics within your circle or available data, you can use that one to model that one. Whereas a model example we can see to learn the model example, or we'll see this example. So what we can see is that I try to put it before it opens up, and I think I try to put it here for our understanding. What we have learned is that T on, T off in expresses I reference, T on, T off. This is the under low speed, right? So we can have higher torque if you maintain this high reference at low speed. It will have T max. So at low speed, once it is crossing that rated speed or rated speed condition, okay, at rated speed, what we can see is that we require at rated speed, over the rated speed, we have only angle control, right? So where current is falling less than this one, the area is less. So if say for same T on and T off, I'm not varying T on and T off. If I fix T on and T off, and I give current reference, at initial current it will have higher torque will come. At later stage, if I don't vary the T on T off, my torque, because area is less, area is falling down, that means my torque is going to fall. Now interestingly, if I fix T on and T off, and if I give current reference and just turn on the motor and run the motor, you can see that it will be having maximum torque. After maximum torque, the torque starts to fall by itself because area is less. And by virtue, this characteristics is very easy in reluctant mode. And this is what vehicle requires. Unlike unlike the other motors, it is easy to get into that one. Now we know T on, T off, high reference. That is sufficient for us to look to that. A minimum example kind of things. Let's say 8x6. We know 8x6. I'll try to breathe this one. I think so if at all you are also having the MATLAB system, you can open this switch machine as an example, and then till now whatever we have learned, we'll try to adapt into this and see what are the things that are available. Okay. Now see, only control parameter is that I just brief out this model. So this is the classical topology. If you open and see the classical topology, right? So it's a two switch per phase topology, and then if you open this motor and I put right click and if I see the mask, look under the mask, okay. I'm going to look under the mask, and if I open the model, you can see here the model is completely built on the characteristics. Okay. So you can see the first equation that I told you is being get that one. And the other characteristic essentially is torque characteristics. You can see torque, current, and theta are the input for that one. And then this is the low torque equation, which is simple mechanical equation. Torque developed to the low torque. So T minus TL by J will give you the low torque equation. Integration of it's a d omega. Integration of that one will give you omega. Okay. So this is a very simplest way to, if you have your practical data also, you can incorporate that. Maybe I'll try for one example. Now here when you come down, what are the things required? We'll see. So I'm just moving to this regulator. You can see a couple of parameters here. Now reference current, initial position. See, since it's 8 by 6 SR, every 15 degree we are having a change, means phases are shifted with every 15 degrees. And with reference to first position, I am just turning on and turning off this angle. So this angle only depends on our logic that people use. Okay, I'll put it. So what I'll do, it depends on what sign convention that we choose. I can choose 0, 30, 60. The other possibility is also you can keep this center in terms of having more negative angles and nothing. People will take from this side as this also is center. So 0 to 30, the generating mode, and 30 to minus 30 will be motoring mode. Okay, it depends on convention. So now here in that model, what people have considered, so turn on angle as or any convention, people can have multiple convention. I think so. This they have used convention from considering from 30 to 30. Reverse way they are considered. So 0 to 30, 60. Okay. They are considered in this way. I'll let it just they are considered sign convention in that way. This. So from 0 to 30 negative slope, from 30 to 60 positive slope. So they marked in that way considering this. This is only sign convention. So in this motor they are considered in that way. So when between 30 and so between 30 and 60, if you turn on and turn off, that will give you positive torque, positive current. So that's what the model is doing. Okay. Now if I double, you can see that I'm giving current reference 50 amps. Now if you actually look into this model, I'm just going into the model for understanding. Fine. So this is omega, from where I'm getting T1 and T off, I'm giving on angle, and this omega I'm trying to get position. Integration of speed will give you the theta. This is integration, and this is conversion from omega, which is coming in radians to degrees. So you can see the radians to degree conversion we have. After that, this integration we are making in degrees. So for every 60 degree, I'm mapping the position information. And within this 60 degree, if I take first phase 0 to 60 degree, I'm turning on and turning off, I'm adding that one, I'll get a pulse. So with that pulse, I'm giving a signal pulse on and off. T on and T off are coming from here. Now current reference is coming from outside. So I'm giving current reference value and I'm giving a band control for that one. This is the gate pulse that is going for. I hope if you understand this principle, that is very sufficient. Now let's try to play with current reference T on and T off and see what will happen. Now I'm just running this model. Now you can see at lower speed, when speed was low, okay, we are putting into the hysteresis current and we have referenced the current to 50 amps. So you can see the reference current is 50 amps. Okay. Now, as speed is increasing, you can see current reference is maximum side. As speed is increasing due to back EMF, it is entering into angular moments. It is entering into, because I am just fixed that one, fixed T on and T off. Please understand how I am not varying the torque. I am just leaving that on T on and T off like that only. Fix it for the maximum. So once I fix the current reference, my initial torque is very high. Okay, I am getting the initial torque 100 Newton meter, and as speed increases, you can see After that, the torque is also falling by itself. So T1 and T off I am fixing and current reference I am changing. Now if I want to change, as we have learned the fundamental point, if I want to change the magnitude of the torque, all I have to do is that I have to increase the current. Okay. Now I try to increase the current and see what will happen. Is my torque maximum is going to come? Now you can see the current value is increased and torque value is also increased. And you can see the torque value. Okay. With the current value, you can see the current value is going higher current, and you can see more torque is produced, and that is helping us to accelerate. So during this, if you observe right now, the rise is high. So what we can see is that by controlling the current, we can control the required. By controlling the current, we can control the torque. And now I'll put it back to the current. This is for learning exercise only. Now what I will do is that if I want to make from motoring to generating mode, okay, all that we have to learn is that we have to switch on into negative slope of the region. So what was the negative slope of the region that we have considered? Between 0 to 30 if you switch on, in this case, in this motor conventions, we can see that it will enter into generating mode. So what I will do, producing negative torque. Okay. Now I'll open and I'll make only changes that I'm going to make the same current, I'm going to make within the first region. Let me check 5 degrees to around 20 degrees. We'll come back to this point of degrees. Now if you open and see that your torque production is actually opposite. Negative torque, we can see the negative torque is coming here in this case. So you can easily switch from motoring mode to generating mode. All you have to do is that you have to change the positioning of the phase, where the position of that one. And if you look to all the phases, you have other 3 phases, and as you see that at angle control mode is entering into angle control mode. So I'm just seeing the 4-phase current. You can see here, it is in angle control. Current is already limited, so you can see it's an angle control. You can see that single pulse mode. You can see that current, all the 4-phase currents are there. So they are contributing individually by phases, and this is the resulting torque that we can see. And once you do the outer loop control, and this reference current is going to come from the torque reference. One example we can show is we had. This was from practical characteristics that we had. Maybe more. So here we loaded with the characteristics and everything. So take it. No. So this is the outer loop. An outer loop is square root is deciding the current required. Now the torque asked, this was a 4 kilowatt motor, 25.5 Newton was the torque question. So torque at the load, that is creating a reference current here. Now there are actually accurate further. This is actually very basic model of that one is that taking the square root of the torque. But if you correlate and bring actual torque to that one, you get very good accurate value of current reference. Now I'll try to stop here and show that for this value of this current. So here we can see each phase torque is limited and the current reference value will decide the torque value. Now if I reduce the torque, if I reduce the torque to half, okay, so let's me put some value for 13 Newton, okay. For this lower speed, 150 RPM, okay. Some issue, the lower speed, proper data we need to build. I'll take my mark. Yes, way back. Draw. That's one of the old the same auto model which we had mathematics before when I was doing 2009-2010 period. We built with a mathematical model. This is the voltage equation and this is the clock flux as well as torque equation. And this was the control strategy that was built. 115. And this T1 and T off. Okay. We can populate based on the angle required. This is that model also somewhere we have. That I'll just try to do. So here you can see the base current energy based on the torque requirement. This is a phase, and if you change the torque value, if you require torque level, then I think so we check. 12 or such, whatever the torque, we already mapped that one into control. Okay, you can see that resultant torque is reduced. So we are getting the resultant torque and the current is controlled. This current value is also reduced. Can you see? So T on, I reference, T off will decide as the required torque levels. And now coming down to one question that people are asking, and that's very essential to us to learn is that how do we fix T1 and T off based on that? Now, what we can see is that I want you to look onto the ripple of the curve. So, the control strategies people start to look, people various people work in a different way. So, one of the way is to identify that you can see this is my current torque ripple. Torque ripple typically we have from 15 Newton meter, which is reaching to 7 Newton meter. Around 7 Newton meter ripple is there. Okay. Now how the T1 and T off angles will help us is that in order to optimize that one, so let's take if I make it 10 and if I keep it to some more degrees towards 30, I'm going towards 30 degrees. That means I'm going here to 28 or something. With this, what area I'm trying to manage and current reference will be changed by the controller. So if you do that part, and you can see that my ripple is going very high. Now 20 Newton meter to almost to 7. So the choice of this T1 and T off comes with optimizing with reference to the torque ripple or required torque per ampere. There's some advanced controls called as. See, there are two control categories. One is performance, the primary performance characteristics, secondary performance characteristics. When it comes to primary performance characteristics, we always work on cost, efficiency, and everything. So that's the primary category of them. The down the line secondary category one based on the application requirement. For example, if you apply reluctance mode for EV, obviously EV application demands torque ripple should be less, noise should be less. In that case, what happens? You have to optimize for that application. How much minimum torque ripple has to be this. So during those strategies, secondary performance, you will identify positions, optimize the position such a way that your torque is minimum, and there is other control strategy called as torque per ampere. You should have for less amp RMS current of less amp, we need to have more torque. That also we have to we can change the values and see. And T1 and T off can be changed as per the requirement. Now, if you do you do higher angle control? I think in the higher angle, everyone look up table and not just for able to find where we can make that look up table. So this is a way of working low, and I'll try to see that lookup table once get that one. So you can make all the combinations of required torque in this one in that way, so that you will understand. Or I'll put my tech pieces that would be. Sorry, I'll show it here on. Okay, you would trace for that what for our convenience I'll show that. To trace that. Okay, um, now we have Stuti, can you send that my thesis that I give? They are sending me Gmail, not I'm sending Gmail, right? Yeah. Fine, good. So just I want to got this is my master thesis. Just want to show you what exactly people try and how that will help us. You can see this is the current vector, this is the table at low speed what should be the torque and what should be the parameter. And this was the torque waveform. And we can see that two controllers have compared. So when stop loss is 35, 33.75 and 56.25. And we also can see that at various angles we get various torque people and everything. So that here you can see the same instances control with different TON and TO. Okay, and we can see that torque people in this case is less compared to this one. So we select and we'll optimize that. These days we have algorithms which have already come mapping with the theta value or TON and TO, where we can get the minimum torque people and all that. So this is a fundamental way of doing changing the values of TON and TO and identifying which phase means where we are getting minimum torque. Now, as you go to high speed, you can vary the T1 and T off angle to get optimal way of identifying the torque signal to be minimum and getting the values. And you can frame a lookup table kind of approach. You can see I have made the T on angle, T off angle required, and I have already mapped. Finally, I controlled is in T off angle control mode. That way we have made a lookup table. So this is the lookup table that we can bring up with reference to change in speed, change in torque, and we can map that one into the model. We can put that into here when we are considering control of that. This is another example. And now, the 2 points that we will discuss is that what we have learned is that by controlling T1 and T off, by controlling T1 and T off and I reference, we can control the torque and we can control. And T1 and T off angle can be selected based on our minimum requirement of torque ripple, whether it's falling within the width. And when it comes to direct torque control or DTC control or guide control, we are trying to estimate the torque getting from these characteristics only, the torque speed characteristics. From that characteristics only, we can get back the value of current reference and we can work on that. So from these characteristics, this people have started to work on that one. For minimizing torque ripple, so what should be the current reference, actual current from this one, and try to optimize the current in that way. So people can work in multiple way to minimize that one. I think so. I've tried some other exercise also. Yes. Right. Another example also can you talk about. Already talk, talk. Anyway, we can the people can start to work with the top required top levels required parameter. So now let's come back to zero. Some of the points that we are relevant to EV is that what we can see is that it is a control is if you understand the parameters of torque, parameters of current, and the slope, DL by dt, way to turn on, way to turn off, you can easily switch between motor and generating mode. This is another key point. Switching from motor into generating mode is easy, and high starting torque, because torque is proportional to square of the current. Obviously, we can get at low speed only we can get higher torque. And unlike DC motor, it is easy to control in this case. For short duration, you can increase the current. And volume required is this, because there is no I2R losses within the rotor. It can have more power with less volume, and it's economic efficient, and we can easily switch between motor and motor. So these are the things that's promising. And ideally, it is matching the characteristics of each vehicle requirement. And so that is another key point of reluctance mode. So though again we need to optimize properly with the torque ripple, torque noise, efficiency and everything, but it's act suitable directly to that one. Other key point is also very essential. If you look at that one, is that we require more constant power region. So for any vehicle, but SRMs are more promising. We can see SRM's speed ratio for maximum speed, top speed to the base speed. Okay, the speed ratio is high. For permanent magnet based motors, it is 2. For induction based motors, it is 4. And if you see that SRM or reluctance based motors, it is 6. That means what? More region is actually high efficient. And if you actually see the efficiency graph of the system, you can see that you have more region of constant power region with efficiency. Constant torque region is very less. That's what we can see. So the use of that one, it's applicable. Although there are hurdles of torque ripple, people are well established. Even couple of my works are in that domain. We have worked on torque ripple minimization and vibrations, also minimizing noise. Still, the challenge is that it's in lapse period. That means it is in not in large production. Any technology from research to the industrial production, if your large production comes, then it's called as close of lapse period. Now, currently, we don't have large productions happening research more, and it is not in large research is done. So now we have to look into large production. When it comes, lapse period is over. Now, currently, by the end of another decade, we can expect that now few of the manufacturers started to do in India reluctance motors. Now they're slowly increasing. The numbers are increasing very slow rate. Now, if manufacturing comes in large scale, obviously the cost and the availability it's going to affect, and it's going to reach lesser cost even than induction motor. So that is very promising. Now it's in lab state. By the decade, we have large production. People can start to use this SRM. And already research for EV application, people have started to use SRM for EV. Okay. There are a couple of manufacturers who already try to build SRM for EV. So that's about the control studies and a couple of examples that we can see here. So this was Aspen Board company, which was in IIT Kharagpur, started by 4 graduates. So they approached during that time, way back in 2019 or 2020 time. So they approached for this reverse smoke control for EV. What they have done is that they retrofitted into a Maruti vehicle the reluctance mode. And they went with this control strategy of current control based method for that one. They were able to do forward motoring and okay. So they were able to do forward motoring, reverse mode condition, all that thing they were able to do easily. And SRM was used. Now the company, all the 4 graduates have been, the company was acquired by another company. It was observed. The idea of that one was putting a reluctance motor into EV. So they have developed and they have executed and they have been given job offer within the company, and the company was absorbed with each person being sold out, giving a share of 1 crore each person was given. So that's a new idea that people are adopting, even industries have start to work. And a couple of other things that people start to work is that reluctance motor they are mounting into the rotor, that is in-wheel drive. So within the in-wheel drive, they have started to deploy, and people are working with the axle-based reluctance motor principle. So they are upcoming promising. And now when it comes to pump load application, other one point that I would like to stress is so I just want to stress on the pump load. I put it here. The pump load, other point that is very, very important for us to understand control strategy, torque is proportional to square of the speed. So torque is proportional to square of the speed. In this case, what happens is that during lighter speed or low speed region, what happens is that unlike your EV or other motor application, you need to have higher torque, T max at the higher, and after that you need to have control strategy. In this case, we know we're able to get T max, keeping high reference, and it has to be controlled in hysteresis. Hysteresis is needed for this application if you want to have higher torque with this one, and that requires current sensors. Obviously, if you put SRM into an EV application, obviously you have to do current control strategy, which can minimize the, which can get the more torque with the, and you need to put current sensors for that one. But interesting point that I've learned and I observed is that in case of water pumping application, this torque during this starting point is actually low. Okay, and because you don't require low torque in the low speed, and this is the rated speed. Okay, then you know. So interestingly, for pumping application, I felt that easily is that you need not have a stress control. So that's what eliminates the current sensors, eliminate that one. All you can do is that T on, T off control, or in case of PWM, what we have used in our case was PWM control strategy. So which was helping us to get zero that one, and we identified that PWM control strategy was helping us very easily in all the parameters that we already looked through that one. So this is very simple to do because for quadratic load, requirement is less. So obviously current requirement will fall, your peak current will fall, your RMS current will fall, all that thing will be very low. Obviously you have to work with the torque ripple only. So you have to choose T on T off in such a way that it can optimize the torque ripple and it can produce the required torque only at the required speed. I think so this is another key point when it comes to variable DC PWM technique, applying for water pumping system, especially for quadratic and pumping load applications. This I'm investigating in other ways also. I'm trying to put in. I don't want advanced control strategies for having for water pumping applications. If you put the simplest control strategies, that will be sufficient, and we need not put current sensors, we need not put any thing. And also, I'm exploring with other kind of motors also for water pumping application that at lower speed, I don't want the rated torque. So, another key point that we can take away. So, the model, if at all have seen the model here. You can put the required kind of outer loop, inner loop, and you can explore the control strategies with this model that's available. If you have practical characterization, then you can incorporate those practical characteristics and you can bring into the system. I think somewhere I have merged a couple of things. It's very difficult to find the files and to show. To one extent, I have showed you what exactly to do. I think so. I can wind up at this point. And if you have any couple of questions and if you have any discussion on this one, I think so that we can discuss both the points. Q&A session we can have. Okay, just.
Thank you, sir, for valuable insights. Sir, no questions from our side.
I hope if anyone started to work on this reference portal, if you have any questions or anything, please you can contact me, no issues. We can use this example. I think so it will be useful for you to understand principles, controls, and there are advanced controls like torque minimization technique or DTC control, vector control also. But now while in for pumping applications, I don't prefer that vector control is necessary. But when you have EV application, you still can do vector control for this reluctance motors. Okay. So that's from my side, and thank you all. And I thank Nasrima sir for being my guide, my mentor, and I always cherish to be with being at NIT Bangalore, doing my PhD. And I thank all the NIT Bangalore faculty, readers, coordinators, and especially the PhD scholars for coordinating and helping out for giving this opportunity. And thank you all. Thank you all the audience for this session.
Thank you, sir.
Thank you. Any comment or feedback from your side also is welcome, and I welcome for any interaction. Thank you. Everyone,
Yes, sir.
thank you.
Good afternoon. Prashant now will brief idea about his work. He will give overview of this area. He's a reading scholar and a guitarist. We don't take too much time. We will finish in 10 to 15 minutes.
Mike. Mike. Follow please. Sir, now. Sir, Mike. Mike.
Good afternoon to everyone. So I am Prashant, PhD scholar at NIT Warangal under Dr. A.V. Giridhar sir. So in addition to Dr. Vijay Babu sir, so I present my PhD work. So me also working on same area, SRM. So mainly I am working on different. So I will give some different motors available for EV applications. So first one is brushed DC motor, brushless DC motor, induction motor, permanent magnet synchronous motor, and switch reluctance motor. So these are the motors available for EV application. So observe this. This table I have prepared from the different reference papers only. So observe this table. So no doubt here PMSM is the very dominating machine now. So most of the EV industry manufacturing companies are using this PMSM only. But problem with so it has own drawback. So it is mainly depends on rare earth material. So it depends on permanent magnets. Rotor part is permanent magnets. So it depends on mainly rare earth material. So in future maybe because of scarcity. So this it will not up to the future demand maybe. So after few years maybe the material won't available at that time. So SRM is the good choice. So but comparatively, so no doubt PMSM is the dominating. So coming to efficiency, torque density, everything will good. So one thing about SRM, so no windings on the rotor part, so less cost and weight is also less. And here one phase is independent on the another phase. So if any one of the phase is any fault occur on the any one of the phase, so we can operate the machine continuously, so remaining phases. So that option is there with this. So SRM itself has some fault tolerant capability, but we can increase the fault tolerant capability further. So if because so here observe this one. So these all the machines. So these all are special machines. So except induction motor. So all the motors are we need converters in between. So suppose induction motor. So if we give the direct AC supply, so it will run. So but PMSM or SRM. So these motors, if we connect direct DC supply, it won't run. If we connect AC supply, it won't run. So we need to control this supply. We need a power electronic converter in between. So we want some DC supply. We need to convert into AC by using inverter circuit, and that is connected to motor. It will rotate. It won't rotate. We want power electronic circuit. So if any fault occur, either open circuit fault or short circuit fault occur on the any one of the switch, one switch failure, so the complete system will be shut down. So we need to operate the machine so continuously, even though if any fault occur on the any fault, either open circuit fault or short circuit fault on the systems. System, we need to operate the continuous. So otherwise, so this mainly we are talking about EV application. So EV, suppose if any switch is failure, so the complete system will shut down. So the vehicle will be stuck in one traffic condition. So to avoid, we need to provide some fault tolerant capability. So we can't identify the fault free fault condition. So even though if identify, so we can't rectify immediately. So we need to provide fault tolerant capability. So default, we need to some mechanism we need to provide in additional before only. So I am working on that one mainly. So already you know the principle already sir explained. Okay, so advantages and attractive features and drawbacks already you know. So applications. So EV application, aerospace application. So SRM, we can operate as generator also. So that's the reason this is suitable for wind power generation also. So we can directly connect a direct PV fed water pumping system. So that So, but we need to improve some essential improvements for SRM. So, first one, reduction of torque ripple, because here both stator pole and rotor pole are in salient nature, double salient nature. More air gap is existing in the machine. So, because of that air gap, so more torque will be torque ripple will be generated. So, we need to reduce the torque ripple content. So many techniques are there. Most of the authors are work on this one: direct torque control, instantaneous torque control, torque sharing function, and MPC technique. So what are the other techniques are available for other machines? So same applicable for here also. So we need to reduce the torque ripple. And and reduction of torque, because of torque ripple only here noise will be high. So we need to reduce the acoustic noise. So this we can achieve at the time of design point of also. So most of the authors work on design point of view also. Next, improve power density and efficiency and enhance the fault tolerance capability and reliability. So mainly I worked on this area: enhance the fault tolerance capability and reliability. So this is the main system of SRM drive. So this is a basic conventional converter. So that is the SRM motor. There is a converter. So basic converter. There is asymmetrical off-bridge converter. So this is the basic control strategy. So to operate or to control the SRM motor, like the torque controller, so to speed control, anything we can achieve. Here, researchers work on different areas. One is design point of view, another one converter topologies. So few of them works on control strategies to reduce the torque ripple, everything. So this is the complete system diagram. So now coming to fault tolerant converter. So these are the different possibilities converters are there. Okay, so for two switch converter and two stage conversion. That means available supply is AC, we need to convert it into DC, then connected again, we need to generate AC and connect it to DC supply motor. So, and we need to consider two switches per phase, 1.4 switches, different topologies are there. So, next, this is one of the topology for SRM drive. So, this is a basic topology only. But here added one more supply to reduce the torque ripple. But this converter doesn't produce any fault tolerant capability. So if any one of these switches failure, so the complete that phase will be shut down. So we can't provide another alternative operation. So but this topology reduces somewhat torque ripple. So in point of view torque ripple, so this work is good. But it won't produce any fault tolerant capability. So next, this is another topology. So if you want, okay. Okay. So next, this is another topology. So if by using this topology, we can achieve some of the fault tolerant capability. Suppose in the positive leg, any one of the switches failure, so we can operate in the inverse mode. Why we go for the inverse mode? Because we know torque equation, torque is equal to half into I square into DL by d theta. So I square. So even though we operate in positive direction mode, negative direction mode, we get torque as positive only. So current torque is independent on the current direction. So torque is always positive with respect to current direction. So we can operate in positive direction or negative direction. So this is not possible for any one of the machine. So this is one of the advantages for SRM machine. We can operate both the direction. So based on that only, so I have selected this these topologies. Okay. Here we generally we can operate in positive direction. So any one of the switches for open circuit or under short circuit fault condition, we can operate in the negative direction. But with this topology, we can achieve only 3 levels. One is plus VDC, another one is minus VDC, and 0 level. We can operate only 3 different conditions. 0 level is not operating condition. So we can operate only negative mode condition, minus VDC condition we can operate. So we can achieve only 3 levels by using this topology. Next one is this is asymmetrical off-bridge, but it's neutral clamp damped asymmetrical off-bridge converter. So with this converter, we can achieve 5 levels. But if any one of the upper switch is failure in this case, so we can achieve only half of the voltage. Means we need to operate the machine with reduced voltage only. So it will lead, maybe it will produce this high torque report. If we continue operate, so it will damage the machine. So that's the reason. So this is also limited. So this is similar to previous one only, not much different. Okay, now. So but instead of two MOSFETs here, consider one switch as IGBT and another switch is MOSFET. So but it's this configuration is same as previous one only, no much different. So with this also we can achieve same 5 levels, but if upper switch is failure, again we get only half of the voltage. We can operate the motor with half of the voltage. So that is the drawback. So I have proposed this full bridge converter. Okay, now so but no doubt this circuit complexity is high compared to previous one, but we can achieve 5 voltage levels and we have different options. So we can operate plus 2 VDC mode, minus 2 VDC mode, plus VDC mode, minus VDC mode, 0 mode, 5 levels we can operate, and so many alternative options are there if any one of the switches failure in this converter. So already we discussed the torque is proportional to I square, so we can operate both positive mode as well as the inverse mode operation. So based on that condition only, I have selected this one, so we can operate in the negative mode direction. So in this case, suppose example, so here first S1 switch A is failure. A is failure. So actually general operation, so for excitation of A phase, we need to turn on S1A, S2A and S7A and S8A. So the current is the phase A winding is excited in the positive direction mode. So if now I am considering S1A switch is failure. So we can operate the machine with half of the voltage with the same positive direction, because so here clamping diode is there. So with the VDC below supply, okay, so D1A is turned on and S2A is already turned on. Okay, S1A is open circuit. So and again S7A and S8A, these two are turned on. So we can achieve half of the voltage, means VDC voltage we can achieve. So we can operate our motor with reduced voltage, half of the voltage in positive direction mode. Suppose if we want full operation, okay, na full performance, okay, without any disturbing, so in we can achieve. So we need to turn on S5A and S6A and S3A and S4A. If we need to turn on these 4 switches, again we can achieve full operation, rated voltage condition as well as rated current condition. But this is inverse mode condition that won't affect any torque direction. So we can achieve like this. So suppose if S2A is failure, open circuit fault condition. So no doubt we can't achieve either plus 2 VDC or plus VDC. So we need to go with negative operation only. So again we need to turn on reverse part. In that way we can achieve negative, we can achieve full performance. So this is plus 2V normal mode operation. Here, if we get one option is there, negative into plus 2V mode. So in positive leg, any one of the switch is failure, upper switch is failure, we have one more option. So next, coming to plus VD mode. So if any one of the lower switch is failure, we have 4 alternatives. 8 alternatives are there. So we can operate the motor with 8 different ways. So in that way, fault tolerant capability is increased. So next, coming to 0 mode, again 6 operating modes are there. So next, so here example, look, here we consider S1A is failure. So remaining 3 phases work as LD only. So rated voltage it is developing. But which phase which is failure, in that phase, so half of the voltage we getting. So with the same direction. Otherwise, if we want to change, so we can operate with the reverse direction. Last one. So similar way, so next S2A is failure. We can operate the machine with the remaining 3 phases, or we can go with the negative direction. So next, short circuit condition. If any short circuit condition occur on the upper switch, so we can't identify. We can't identify. We can achieve positive direction with full rated condition only, because triggering pulse is same as which is conduction mode. Even though short circuit is also same as conduction mode only, we can't identify the short circuit condition. So if S1A is failure, we get full operated voltage. But when we want to reduce voltage, at that time we can identify the fault condition. So we can't operate reduced voltage. Because for reduced voltage, we need to turn off S1A, we need to turn on S2A. But already S1A is short circuited. Even though if we give pulse for S2A, so the complete leg will be short. So we can't achieve half of the voltage if S1A is failure. At that time, we need to operate in the reverse direction if we want half of the voltage. So this is one thing. And if S2A is failure, we get only half of the voltage if we turn off S1A. Even though if we turn off S1A, again we can achieve full voltage. So short circuit condition, so not affect much to operate the system. So if we want different voltages, at that time only we can identify. Otherwise, we can't identify. So if we follow like this, so we need to balance between the capacitors. So because here for neutral counting circuit, okay, here two capacitors we are using. So we need to operate balance condition. So for that, first we need to calculate the potential difference between capacitors. So EVDC. So here two different conditions are there that EVDC maybe increases or decreases. Okay, so if it decreases, we need to follow. Here we have 8 operations for plus VDC mode. So we need to select based on the EVDC condition. EVDC decreases, we need to select either 1 or 4 or 8 or 6 based on the voltage. So again we want plus voltage. Okay, so either we go with 1 or 4. But here again the inverse mode operation or positive mode operation, again we need to select only one, either one. For positive mode, again we need to select first mode. And for negative mode, we need to select fourth mode. This 1, 2, 3, this is from this table. So here total 8 possibilities are there. Based on the EVDC voltage, we can select the particular mode. So we can give these signals or we can trigger the switches according to this condition. So we need to maintain balance between the capacitors while doing this one condition. So these are the simulation results. So this is normal operating condition. So here all 4 phases are healthy condition. Okay, now so we get rated speed and rated torque. So but if we consider any one of the switches failure, S1A is failure. So here I created fault at 0.3 seconds. Okay, so from 0.3 to 0.32 seconds. So switch is under fault condition. So in that case, we achieve only half of the voltage because upper switch is failure, open circuit. Already S2 is turned on. Half of the voltage we can achieve from that phase. But voltage is reduced because of the voltage reduction. So no doubt we get some torque ripple. So machine will operate continuously, but we will get some more ripple, more content, more torque ripple. So observe that the torque characteristics at 0.3 to 0.32 seconds. So we get more torque ripple. So later again we need to either operate in the negative direction. So again we can achieve full torque without ripple. So next S2A is open circuit condition. So again if S2 and this is lower switch. If lower switch is failure, so completely phase will be shut down. So observe the again 0.3 to 0.32 seconds. So one particular phase is not there in that. So because of S2A, lower switch is failure. So again in that case we get high torque ripple. So we can operate in the again negative direction. Our system will continuously run. So we have that much that option is there. So in that way we increase the fault tolerance capability. So this is short circuit failure. So we can't observe the short circuit condition because short circuit condition is nothing but turned on condition. We can even though fault occur on the switch, we get full performance. Torque is as usual only and speed is also as usual. If S1, S2 is failure, we get half of the voltage. So your torque and speed will be reduced to half of the voltage. So and some analysis part. So how much fault tolerant capability this converter have, we need to calculate. So these formulas I took from the reference paper and some textbooks. So we need to calculate reliability of the any electrical circuit or any electrical equipment. So it is mainly follow on the exponential function R of t is equal to e power minus delta t. Here delta is nothing but failure rate of the equipment. Any electrical equipment or electronic equipment, it has own life and own failure rate. So here any MOSFET switch life is or failure rate is lambda is equal to 10 power minus 6 per hour. 10 power minus 6. That is the failure rate. That is standard value. Okay. So next and reliability function R of t is equal to sigma k is equal to 0 to n minus 1 and lambda t power k by k factorial into e power minus lambda t. Here lambda is the failure rate of the equipment and switch. Here our equipment is switch. Okay. So here that is the lambda is the failure rate and k is the how many possibilities are there if the switch is failure. So without disturbing any performance, how many ways are there we can operate? So that k gives that one. Okay, k is the value of number of possibilities. Already we discussed if S1A is failure, we have only one option. If S2A failure, we have so many. For 2V volts, only one option, one possibility is there. For 1 volt, we have 8 possibilities are there. So k is the possibility rate. So in that way, we can calculate the failure rate as well as once we know the failure rate, reliability, we can calculate the failure rate of the converter. So that Q of t is equal to 1 minus R of t. So first we need to calculate lambda value and how many possibilities are there. We need to calculate k value for particular mode. Okay, we need to substitute both values in that equation. So we get reliability of the converter in that operating condition, in that mode. So later we can calculate the reliability of the function. So and here I consider for 5 years period over t is equal to period of the converter and how much time period we need to consider. And after 5 years, what is the life of the converter we are calculating. So here I am assuming 5 years time period. So 5 years means 5 into 365 days, 365 into 60. So that hours 60. So that we consider the value. So same value I substitute in the equation. So we get reliability as well as the fault tolerant capability for each condition. So S1A failure. So at 0 mode condition, at 0 volts mode condition, to 1 volt mode condition. So similarly S2A is failure. At 2 volts mode, how many possibilities are there? What is the failure rate? What is the reliability of the converter? So in that way I calculated each and every mode and each and every condition. So finally this is the conclusion. So all for plus 2V mode, all switches have probability of failure S1, S2, all the switches are same equal to 0.1607. So after 5 years, the failure rate of this converter is only 0.16. If we want only plus 2V. If we want plus 1V, 1 volt, that means our reduced voltage if we want, so we can, that failure rate is very, very less, that is equal to 0.013 and 0.06 for some other lower switches. So next, if we want 0 volts mode, so that is very rare condition. So, and short circuit condition, we can't identify, so we can achieve full performance with the short circuit condition. So this is a complete table information. So one switch failure, either open circuit condition or short circuit condition, and we want to which mode, either 2 volts mode or plus 3 volts mode or 0 volts mode. Okay, now so this is the information about the failure rate at each condition and each switch failure. So this is another asymmetrical of this is my proposed converter, and this is the asymmetrical of general basic converter. So compared to this one, so this failure rate is very low. Reliability is very high, this converter. So this feature is very, very useful for EV application. So because safety is very, very important for EV application. So already Vijay Babu sir told about machine data, how we can extract machine data. So here we have two approaches. Sir also told same thing, me also same. So for a design point of view, we can approach finite element analysis method. So this method is applicable at the time of design only. Once we design the machine, we can't generate the data by using software. So we need to go with experimental setup only, similar to induction motor. Suppose if we want some performance characteristics, we need to do black rotor test, no load test like that we need to do. Similar way, if we want data of this SRM motor, we need to do experimental setup. So initial stage at design point of view, we can follow with finite element analysis. So this is the voltage equation. From this voltage equation, this is very simple KVL law only. But here inductor is not constant. Inductor is variable with respect to rotor position. So the other reason L is inside the derivative term. So previously, suppose other machines we can write V is equal to R into I plus L into di by dt. So here we can't put it because L is not constant value. Here L is the variable value with respect to rotor position. So that's the reason here d psi by delta is the perfect. So here from this equation we want to flux linkage characteristic because we want to control the motor. So we need data, machine data. Without data we can't control the motor. So either torque control or speed control, we want the data. So data is mainly flux linkage characteristics, inductance profile, and rated current, rated speed, how many poles are stator, how many poles are rotor. So everything we want. So mainly from this experimental setup, we can extract flux linkage characteristics. So this is the equation for flux linkage characteristic. In this, after this equation, we want to only already resistance we can measure, phase winding resistance we can measure. Okay, so but we want voltage and current with respect to one rotor position. So coming to other machines, so any no need to take rotor position. So we simply block the rotor and we can calculate voltage and current. Under short circuit and open circuit condition, we can take the data. But in this case, not possible. We need to take the data at each and every rotor position. At 1 degree, each and every 1 degree. So we have 30 degrees portion. So as already sir told, so we have 60 degrees period because 8 by 6 pole. So that 360 by 6 is the 60 degrees in the polar. Okay, now so in that 60 degrees we can operate generating mode as well as the motoring mode. So for 30 degrees go for motoring mode, 30 degrees go for generating mode. So each in that 30 degrees we need to do experiment for each and every one angle, 1 degrees. So this is the experimental setup. Nothing. So here machine winding is connected to supply with switch. So we need to block the rotor and turn on the switch. We get voltage data and current data by connecting the DSO. It was at that rotor position. We need to note down the value, or we need to take the graph of voltage and current, because your current is not suddenly. This is with this machine it behaves as an inductor. Inductor doesn't allow the sudden changes in current. The current is gradually increases from it reaches to steady state value. Okay, so we need to take complete portion. So later we need to do analysis and we need to apply those values in this formula. We will get flux linkage characteristics for each rotor position. So later we need to calculate flux linkage value by integration part. This is the Simpson rule. So by using this formula, we can achieve the flux linkage value. Because integration is there in this equation. This integration part we can simplify by using this formula. So these are the hardware experimental setup. What I did. So same circuit I have connected. So this one. And so we achieve these graphs at different rotor positions. One is the voltage, another one is the current. So by using those voltage data and current data, so we can calculate. We need to calculate the flux linkage value at each position. Later, we need to keep all the values in Excel sheet. So we will get this type of characteristics. So from this flux linkage characteristics, we can achieve inductance profile. Okay, so from this inductance profile and flux linkage characteristics, we can achieve. We can get torque characteristics. So once we have this data, we can control any motor. So with this, I conclude my. So thank you. I didn't complete the PhD.
He's asking about the motor.
I am designing control. Simulation part over, so I am working on hardware part. So hardware part also without integrating the motor, I have developed I show results also that time. Not integrated. Again, set of control for the set of control. DSP. But but in this control, same thing. This control, GIAN T of GIAN T of yes.
Those are
from this period to the period, same
Like for current reference, you are generating like
EAD controller. Water position, input of data, we can take that data and convert it into speed. That water position is converted to speed. And we need to generate the torque, reference torque, and from the reference torque, I torque. So again, that is give the actual switching position, and that is generate one particular voltage value.
concentrating on faults.
Me, I am considering
Faults are no difference. All
actually, all control capability is more compared to other machines because here each page is work on independent.
how you are operating this. Switches fails
Because torque will be high now. DC it will affect the DC winding DC current rate current rate. So because of that, maybe switch failure is high. So we need to protect.
So you again have to replace the converter.
Yes. Very high. Motor cost is less, but complete drive cost is high compared to other machines. So the other reason
you got the phone number converter.
the efficiency won't affect. Switching losses very less. Switching losses are very less.
Actually, problem is that whenever you are using this converter and you use for no load only, because as you assume that for EV application, that is a loaded condition.
Loaded condition.
So loaded condition, so there will be a burdening on the switch. Okay, anyhow you explain as per your meeting. I am not actually but as you are passengers are sitting in the car and even car unable to pick up.
Yes, sir.
Because again that churn wave the switches are damaging acting as a short circuit and that burden might be there on that other switch.
But
Maybe okay, for your level okay fine. So we are not thinking like that. Okay, but you will learn.
from 30 to 0 to 30 degrees.
So in between only you are thinking.
Each 3 degrees I consider total 10 position. I don't know the position actually. Saving the voltage. Okay. Like that, normally 10, but you don't have the total data. Oh, no.
Actually, the position,
Sir, actually, we know position. Otherwise, no use of the data. So, for that one more setup indexing aid. So, in that, some marks are there on the indexing aid. Total position markings are all available. So, we need to fix that one. At that time, we know how where we are putting the rotor position. Already we know the difference. From that, I will go to sure.
actually, here we have studied that
That video is absolutely
how you are
that part when by doing so I took one video. So that is very changed. This video.
so that it should be like this target for rated current, right? So you are actually targeting for rated current.
Yes.
Like below that, okay, you are checking, but however, your intensity is for rated. Because you are keeping the EMF is 0.
Yes.
And that's why you are watching that rotor.
Yes.
So means you are keeping the rated value and then finding the
Other participants. Next session going to be started 2:30 in the same by Irupati sir. That was a fantastic presentation. Thank you for your time, Vipashan. And thank you for participants patiently also. Thank you.
It has been a long time since we met in this way. It's just a day, but it feels much longer than that, isn't it? Anyway, so I hope you all had lunch, and we will be doing this is going to be slightly shorter session. We'll do almost 2 hours, mainly because of the nature of the topic. So the main topic for this session is futuristic. What are the opportunities and challenges that we have in using AI for condition monitoring? Okay. So how many of you here had a chance to see the demo yesterday, like in the Center of Excellence, when the gentleman showed vibration? So everyone, probably you too did not see it. Okay. Okay, so that is good. So that will help in this activity. Anyway, so the outline, I have 3 major bullets in the outline. The first one is an announcements, couple of announcements I have, and they are reasonably significant. And then there is a quick review where you will be helping me recollect what ANN is all about and what so that is the idea. And then we will dive into opportunities and challenges. And because this is the session after lunch, this is the most difficult session to instruct, especially when we have some excellent food provided by the guest house. So, so what I am planning is to make you all work in smaller groups, not by sitting but by standing. Okay, and that is why we brought a couple of boards. So we will have, and we will also practice presentations at the end of this session. So anybody who is into PhD or masters, they will be given preference for presentations. Teachers will be taken back seat because they always love to talk. I am like that. And then students will be given preference. Okay. First announcement is about publication avenues. So this came up while I was talking with a few of you yesterday. And then I realized that, so for the field, like condition monitoring, there are a few good avenues that you can explore publications. There are definitely journals and transactions and magazines, but I am focusing on conferences. So there is a conference called IEEE Transportation Electrification Conference. And this is a conference that happens around the world, region specific. So there will be one conducted in North America, one in Europe, one in Asia Pacific. So the Asia Pacific one is the one I am presenting here. And this year it's happening in Singapore between 25th and 28th November. You still have the call for papers open. I hope many of you would be considering to submit your work if you are at that stage. I mean, if you are the initial stage, then it might be challenging. But if you have some progress done already, then this is a great opportunity. The second conference, which is exclusively on diagnostics, is a conference that's very popular. The only drawback of this is held typically in North America or in Europe only. Okay, so this is a little bit of travel for you. But if I can come all the way from Vancouver to India, you can come all the way from India to the US, right? There is nothing. It's just, it's up to you to decide. So this year it's happening in Dallas in the USA. And this is a conference which is considered of high regard in our field, in this field of research. So if you want to establish yourself in this field of research, then this is an avenue that you should consider actively. And just for your information, if you go to any of these conferences, they are reasonably big. So upwards of 1,000 participants. So you will have lots of opportunities to initiate interactions. Attending such conferences also will need a lot of preparation. Other than technical preparation, you have to identify whom you need to talk to. Because when you have thousands of people, you may not be able to talk to everyone, right? So you have to prepare ahead of time which person, which group you need to talk to, etc. The last conference I want to talk is about the Energy Conversion Congress and Exposition. This is a big conference as well. This also happened, I think, happens region-wise. I'm not too sure if it is, there's one Asia Pacific maybe, ECCE, but I am focusing on the North American edition of it. This year it's happening in Philadelphia, but the reason why I brought this up is because in 2026, it is happening in Vancouver. So that is closer to where I come from. Okay? So I have given you enough advance notice or invitation, however you want to think, and I expect you all to be there in 2026. Okay? So this is also a massive conference, upwards of 2,000, 3,000 people typically. So it's a very big conference. But because it's going to happen in Vancouver, and typically it happens in fall, autumn season, October. And that's a nice time to travel. Okay. So this is the first set of announcement I have. These are just 3 conferences I'm presenting. There are many more, but especially the second one is something quite relevant. The first one I thought is something very soon, and it's close by, so you can explore. And the last one is simply because it's happening in Vancouver in 2026. Okay. Then the more important announcement, now that we have come to the 4th day of the workshop, tomorrow is the day when we will have our exams. So there is an exam for this course too, because all these days you have been happy, right? So we have to do something to change that. So I do not know why my animation is all the upwards. There will be an examination tomorrow. The exam will constitute a portion of the course grade. The lecture attendance, labs and demonstration, they're all part of the course grade. Okay, so you will be given a pass or fail grade, if I'm not wrong, by the end of the workshop or the course. The exam will be a written exam, so you will be having some time, given some time, questions, and you will be expected to write answers. The questions will be numerical type as well as conceptual type. So when I say numerical type, you can, so we have discussed 3 algorithms so far, KNN, PCA, and basics of ANN, right? So you can expect questions on these 3 algorithms. So I will give you a data set. I will ask you to find the nearest neighbor. Okay. I will give you a data set. I will ask you to find the principal component. I will ask you a network, a neural network, and I will ask you to calculate the prediction at the end of first forward pass. Or I will ask you to calculate the rate of loss, change of loss function with respect to weights, dou J by dou W, like that. Okay, so these are typical numerical examples. The size of the numerical problem will not be massive, as if in a real world machine learning, this is a pen and paper exam. So it will be more manageable, but you will be still expected to do some calculations. So please bring your calculators if you have. Otherwise, you may have to use your cell phone. Okay. So if this has already scared you, I have something that will calm you down. You can refer to resources during the exam. It's not going to be, because it's just a short-term course. I don't expect you all to have, remember things. But the only constraint you have is you can only refer. You cannot ask for an answer from another entity. When I say entity, this is now taking different dimensions. So usually we say don't discuss with people, right? But nowadays there is much more than people that is available out there. So you are not expected, you are not supposed to take help from any entity. Okay. So that is the restriction you have. If I do not know exactly where the exam will happen, but it will happen tomorrow after lunch. So the logistics sirs will coordinate. And, it will be a straightforward exam. It will be nothing beyond what you know and what you have discussing. It will be an MCQ. So the questions will have few options, but say, for example, a numerical problem, but there will be 4 options. And if there is an MCQ, then always we will have negative marks, right? That's the standard, right? No negative marks. Okay, no negative marks. Okay, so you just have either 1 or 0. It will make life easy for grading. Actually, if I have negative marks, then it makes my life difficult. Anyway, so these are the 2 major announcements. Any questions at this point about the exams? Yes, sir. We have been sharing materials. So I will share the slides as well via WhatsApp. I mean, my slides are all blank slides, so I don't know how much it will be useful, but still, I will share the annotated slides, okay? So that the MMF permeance analysis can be a 1 question. Okay, anyways. Okay, so these are the announcements. Is there any questions for me at this point, or shall we continue? Good? Okay, fine. So we are going to talk about opportunities and challenges. So I want to show you 2 images. It's the same space. So these are the opportunities you have. You may have to overcome some challenges. So do you understand what this is? Snow. Okay. So this is how the campus was when I left for the workshop. So 1 week ago, this is how it was. So I'm not complaining about the heat here. At least not yet. Anyway, so first thing we will do is we'll do a quick recollection of the ANN procedure. The general basic procedure that we discussed. I know you all had lunch, so I'm going to let each one say one thing about the procedure. Okay. So we are going to start any random place. Anybody can go first. Whoever wants to go first can go first. And then I will jot down whatever you say, and then we will rearrange to put it in a sequence after everybody has mentioned. Okay. So what I want you to say is, what are the steps involved in, let's say, if you want to perform machine learning or using artificial neural network? What are the steps involved? Okay, so whoever wants to go first, please raise your hand. Okay, so we will go with that person first. So I see Swapna madam raising her hand, please. Did I say your name wrong or correct? Okay, that's good. So one step, any one step, it doesn't have to be in the sequence. Collecting the input data. Okay, this is a very loaded word, collecting the input data. So we will discuss this later on. Okay. Next, another person, maybe. Initialize weights. Okay, wonderful. Everybody will get a chance, so don't worry. Okay, so create a training set or train the model. So you are saying train the model. Okay. Train the model. Okay. Yeah. Extract features from raw data. Okay. Selecting hyperparameters. Let me just check. Okay. Number 5, selecting hyperparameters. Can you name any hyperparameters? Like not you, but anybody? Like any of the hyperparameters? Do you remember? Number of neurons in the, so basically size of the layer, number of layers, all those things. Okay, that's good. Good. So you all remember that. Wonderful. Yeah, please. Okay, so create a network is what you are saying. Yeah, create a network. So I'll put it that way. Okay, so I'm just rephrasing what you are. A neural network by setting the parameters. Basically, how many neurons should be there? What are the defining the input layer, defining the output layer, all those things. Okay, that's good. calculating the loss. Okay, calculating the loss. Okay. Deciding on activation function. Wonderful. Does anybody remember the activation functions? Some of them. Okay. 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 Thank you. Deciding the activation function. What I can understand is you all are having much better memory than I do. Deciding the activation function. Who has to go next? Devdarshan sir. If you want time, you can take some time. It's up to you. Okay. Error calculation. Okay. I think the error calculation is already mentioned, but okay. So I will just write optimization algorithm, and we will algorithm. I will write error calculation for the time being, and then we will discuss this. That you already spoke, right? No, you did not say anything yet. Okay. Regularization. Okay, wonderful. Regularization weight or regularization formula and choosing regularization equation and its appropriate weight. Regularization. Does anybody remember why we do regularization or why is it important in ANN? To avoid or to mitigate the chances of model getting overfitted. Okay. Yes, sir. Back propagation. So, okay, so that's a term. Yeah, we will come back for second round later, but we'll first finish to creating confusion matrix. Wonderful. Confusion matrix. Okay, that's nice. So maybe few last, anybody else that is yet to speak? Forward pass, okay, back propagation, forward pass. So these are terminologies that are not necessarily like the steps. They are part of activation function is already mentioned. So we have that. Deciding the activation function. So that is also there. So I think, so calculating loss is just calculating J loss. What we need to do is we need to find the change of loss with respect to weights, right? So dou J by dou W and update the weights. So that is back propagation. So that is what we are doing here. Okay. So if, I mean, all the steps are captured, just that the sequence might be out here. Usually we will collect, when we say input data, it's a little bit misleading. So we will collect data from environment, from a physical environment. So it is usually not necessarily the data that we will feed into that ANN model. It can be, but it is not guaranteed. So we can call this as raw data. Okay. Extract features from raw data is good, but it misses one step. You need to do data processing before you can extract features. So what is data processing? Say normalization or eliminating noise, some of the things. Okay, so they are, so usually when you want to extract features, before that you do data pre-processing or data processing. Okay, and then you extract features. Okay, once you have extracted features, that is your data set, then you will split it into training set, validation set. Okay, so once you have the training set and validation set, you will select the hyperparameters, you will create a network, and then you will initialize weights and bias. Then you will calculate the loss through a forward pass. So this is basically forward pass. Okay. So the activation function will be decided when you create the network. Then you will do a back propagation to calculate the change, but you would have decided the optimization algorithm. I don't know what one of you meant by error calculation. Maybe it's same as the loss function. I'm not too sure. Maybe it is. I'm not too sure. Then you will also, in the loss function or in the cost function, you will add a regularization with a weight so that you can avoid overfitting. Okay. Then once we have done that, so this is just one loop. So we have done one epoch, right? And then we repeat it multiple times until our loss function goes down in value. And then we get a good prediction accuracy. Then we stop, we use that model. We use validation set to check the accuracy. Once we are happy with the accuracy with validation data set, then we deploy the model for actual field testing. Okay, so we are all able to recollect the methods. So that's good. So overall, I can say like this, some of the steps involved include data collection, data processing, feature extraction, and then choosing the network, basically choosing hyperparameters. Defining the network basically, and then training training comprises of the whole process, calculating the loss, optimizing it, all those things. But once training is done, when we have a reasonable acceptable accuracy, what we will do is we will capture the time taken for training, we will also make a note of the computational resources needed to carry out this training. Okay, and then we will test the trained model with validation data set. We will check its accuracy. So basically, training will result in some accuracy or performance parameter, training time, and training computational cost. So there are three things. One is training accuracy, which is the performance. So training performance, training time, and training cost. So these are the three things we will record. And then we will subject the trained model with validation data set. For the validation data set, we will check what is the accuracy or performance, what is the time, what is the computational cost. Okay, so we will record that. Typically, validation performance would be either equal to or worse than the training performance. Okay, that is the general expectation. So is this clear? Then finally we will deploy the model and we can say with some degree of confidence that this is the percentage accuracy we hope to get when given an unknown data. Okay, so now that I have spoken a lot, I should break things up. So we are going to do an individual activity now first. So this individual activity is a quiet activity. That means you cannot talk to anyone, but you are supposed to take a piece of paper and pen. And what you are going to do is, the major purpose of running such GIAN workshops is, of course, to introduce you to newer topics, to get you started or to help you go one level up. But the major purpose, the overall goal, is to inspire you to pursue activities in this field. Okay? And I am a very confident, positive looking person. So I believe that I have already inspired you all, that come Saturday, you are all going to start your work in this field. Okay? So that is my belief. I may be wrong, I may be right. Only time will tell that. But this, with that belief, if you all decide to carry out research in this field, so this is an individual activity. You are going to imagine that there is no one else around you, just you. What challenges do you foresee from your perspective? Okay, if you have to carry out this research in this field, or if you have to pursue this future, what challenges do you foresee that might inhibit, that might stop, that might obstruct you from proceeding? Okay, so what I want you to do is take a piece of paper, pen, whatever you think, jot it down. How about 5 minutes? Okay, 5 minutes. So from your position, so if you are working for an institution, then from that setting, from that environment, what is the limiting factor? If you are a student, what is the limiting factor? So put yourself in your current environment and then write down the challenges. Okay, 5 minutes. Does everyone have paper and pen? Okay. Anybody needs paper and pen? Okay. So there is no right or wrong in this exercise. Whatever you think is going to prevent you from carrying out research in this field, put that down. Okay, that's the whole thing. It's your perspective, your view of what you believe might be obstructing or stopping you from doing this. So you have 1 more minute, and then we are going to do another follow-up activity. Okay, so 1 more minute. Okay, it's time. So you can stop writing. And I see that we have almost a 50-50 split between students versus non-students. So that's very good, because the next activity is what I call as a pair and share activity. But you are now going to relinquish the comfort of your seats, and you are going to pair up with, so if you are a working professional, you are going to pair up with a student. Okay, I see. So no two students or no two working professionals going to be in the same pair. Okay, I think one group might have, one or two groups might have 3 members, but that is how we are going to do. Okay, so you can stand, pair up, spread out, and then what you are going to do is each of you is going to exchange at least one topmost challenge in their mind that might prevent them from pursuing this research activity. Okay, so if there are 2 people, each one exchange the topmost challenge first. Then if there is still time, they go to the second challenge. Okay, so you will again have 7 minutes, okay, to do that. So 1 minute to pair up, and then 5 to 6 minutes to chat. Okay, so no two working professionals can be in the same team. So each one has to identify a student, and then we are going to pair up. Okay, so quick. You are going to discuss, so please spread out as much as possible so that you are not interfering with another group's discussion. You have this is a reasonably big space, so you can always move around. And
డెఫినెట్గా ఇది చేయాలి అది చేయాలి. ఫస్ట్ పాయింట్ ఇది
అంటే ఫస్ట్ మనం
కోర్స్ అనేది ఏమి తెలియదు. కోర్స్ ఫ్యూచర్ మెచ్యూరిటీ ఇది నాలెడ్జ్ ఎలా ఉంటుందో తెలుసుకోవడం స్టూడెంట్ చెప్తాం. ఫ్యూచర్ స్టెప్స్ అంటే అన్ని ఇస్తాం. సెన్సర్స్ పెడితే ఏది సెన్సర్ పెట్టలేము.
ఇన్సైడ్ మనకి మిషన్స్ ఇన్సైడ్ మనకి
మెషిన్స్ ఫ్యూచర్ ఫ్యూచర్లో ఏం యూజ్ చేస్తాం? ఫ్యూచర్ ఎలక్ట్రికల్ మిషన్ అప్లికేషన్స్
సైడ్ కూడా మనం యూజ్ చేసుకోవాలి.
ఫ్యూచర్ అప్లికేషన్స్ నా దగ్గర 10 స్టూడెంట్స్ ఉంటారు. ఒక్కొక్క అప్లికేషన్ ఇస్తాను. మీ పాయింట్ ఏంటంటే మీరు పర్టికులర్ చేస్తారు. నా పాయింట్ ఆఫ్ వ్యూ
మనం ఈ సైడ్ అప్లికేషన్స్ తీసుకున్నప్పుడు ఈ టెక్నిక్ మనం అట్లా
అన్నిటికీ అప్లై చేసుకో. ఫ్యూచర్ అప్లై చేయాలంటే ఫస్ట్ ఛాలెంజ్.
How are you doing on time? You need some more time or you have time? One more minute, maybe 1 more minute? 1 more minute? Okay, 1 more minute.
ఆ పాయింట్ ఆఫ్ వ్యూ
So I think thanks for the active discussions. So now I'm going to take your help in summarizing the challenges that you have identified. That's what I'm doing. I'm going to write down the challenges. So what I want you to do is to share at least one challenge. Each group is going to share one challenge because I foresee many of them would be similar. So that's why we are going to go around. And then there is still some more things to add. And then we can share. Okay. So we'll start from the rightmost. So please, one challenge that you have identified. Can you please repeat? So, knowledge gap. Thank you so much. So, next group. Yeah.
That is what are experimental setup for
So, lack of facility for real data. No? Okay. Lack of facility for experimental data. Okay, thank you. Third group. Can you please elaborate on that knowledge?
All the things we need to have coding the same way for application.
So in some sense, it's knowledge gap. Any other challenge that you have thought of? These two. First, okay, that's fine. That's fine. That's fine. It's okay. That's the idea.
Knowledge in hardware and software like that.
Okay. Knowledge gap in
hardware and software.
Compatible models.
Compatible models. Want to know which one is suitable for the suitable. Those kind of details. Like when we say knowledge gap, it's like the details, not the top details. Yeah, that's understandable. Okay. Time and resource constraint. Expert for creating fault transfer. Experimental setup. The group that mentioned about the lack of facility for experimental data. Right? Okay. So anyone else wants to? Anyone can add now. So now that everybody has taken one chance. Problem identification. So within this realm of monitoring or propulsion motors, what specifically would you want to work on, right? So problem identification, narrowing down the focus, so kind of problem identification. Okay, I do not know if this is okay. Next one, anything else? Cost. Cost and practicality. What do you mean with practicality?
It's real time how well it works. For example, some electric vehicle application. Basically, how this will suit for in person because the car overall cost is going to be huge for doing this research implementation.
Yes, practicality from implementation perspective. Okay, cost is a constraint. Should be a constraint, otherwise we won't do well. Anything else you want to add?
Mathematics aspect. Algorithm kept trying to do if I am using different algorithms. This conceptual behind that, for example, GIAN and algorithm,
Knowledge somewhere here. I mean, knowledge somewhere here.
Nice. Nice.
Okay, so these are the challenges. Okay, these are the challenges that you have identified, right? What I'm going to do is I'm going to let them be as they are for the time being. We will discuss them in a few minutes, but let us recollect the steps involved in implementing, say, in an algorithm. Let us see if you can come up with identifying each step of the way. Okay, so it can be a knowledge gap. For example, I will give you an example. So step 1, data collection. What challenges do you foresee here? So for example, you have mentioned lack of facility for experimental data set, and then expertise to create experimental setup. Okay, so these are all challenges that will impede data collection, right? And also cost. Sometimes you may not have the budget. So you have to create a failure, but which is still safe, right? So you have to, yeah. So that's the first step in implementing machine learning model requires data collection, and in order to collect data, you cost prohibitive for setting up experimental work, or experimental test bench is expensive. And then expertise, okay, cost, expertise, okay, even expertise in creating this, okay, expertise required. Okay, for the time being, let us assume that these two constraints are not there. Okay, so this is what I'm going to do. I'm going to say every challenge is not there. Assume, like how you did 4 equations is 2 equations, right? So I'm repeating what you did. Anyway, so assume that the experimental facility is available and you have the expertise needed to create that setup, make it work in a safe manner. And for the time being, let's even say cost is not a major constraint. Okay? Do you still foresee any problem with data collection? Okay, so data collection, these are definitely constraints, challenges, but even if you can overcome them, what challenges do we have? The collection of data itself might not be as accurate to a practical or a real world situation. For those of you that attended the demonstration yesterday, for a lab grade motor with an high accurate sensor, we were having lots of challenges, right? So positioning of the sensor, making sure it works fine, and so between healthy case and faulty case, the sensor must be in the same position to ensure that the vibrations have been picked up at the same point, right? And so there are many challenges even if you have an experimental test bench while you collect data, right? So what I want you to focus on for briefly right now is, okay, these challenges will definitely exist, but if you assume them to not exist, even if you have access, say for example, tomorrow I invite you to my research lab and I give you all the facilities, what challenges do you still have is the quality of data collection, data collected, comparing it with a real world situation. So can you collect similar data from real world versus the data that you can collect from a lab environment? Or how close to real world situation can your lab experimental test bench be when it comes to data collection. Okay. So from a propulsion motor perspective, let me give you a clearer picture. So in all the examples that I presented with experimental data set, I said I collected 15 seconds of data, right? How easy do you think would it be to collect 15 seconds of steady state current data from a motor that is being used in an electric vehicle? So what is 15 seconds of steady state data from a lab environment? My motor speed, my motor load are constant. Right? Am I correct? That is what we are as steady state condition means for us. I have collected 15 seconds of data. In a practical environment, if I have to collect the data from a propulsion motor of an electric two-wheeler or a passenger car, how easy would it be to do that equivalent data collection? 15 seconds of steady state condition. What is your expectation? Like, do you think it would be consistent, or do you think there will be already some variation either in speed or in load? Some variations will be there. So now what we have is we do not know how much time we will have to acquire data. So basically we are going to collect data. Let's say if we collect for 30 seconds, it is not steady state anymore. Or over that window, it is not one steady state. It is multiple steady states probably, and some transients. So we have never explored that even at the lab setting, right? So now even if you have the experimental test bench, you may not have a data collected which simulates real world. So when you have an experimental test bench, it is important for you to ensure you are collecting data in a manner that is as close to real world as possible. For example, the demonstration that we saw yesterday, the motor was mounted on a rigid frame, but it was not bolted to the table. If you go to any industry, that is not going to be the case, right? You will never see a motor just by itself. I mean, in some applications you may see in some sites, but in a factory setting, in field, that is not the case. It's rigidly secured. So when you collect data, even if you have a test bench, it is absolutely important to collect data which is as close to real world as possible. Otherwise, no matter how expensive equipment you have invested in, your model is not going to be implementable at the end of the day. That was one of the challenges you said, right? So this is one aspect. How about certain parameters in data collection, like sampling frequency? How do you know what is appropriate? So if you have an inverter driven motor, if the inverter is being switched at, let's say, 4 kilohertz, what should be your sampling frequency? How would you filter out the signal? Okay? So these kind of technical challenges exist in the first step, data collection, right? So this is the first step, and we have some challenges identified, technical challenges. So next step is data processing. So the vibration sensor is a great example that we could see yesterday. When we collected data from it, there was not just vibration, there was a lot of noise. So we have to do signal processing right at the front end without eliminating the signals of interest. So what does that mean? Our sensor should be having high signal to noise ratio, and our algorithm should be good enough to extract the required signals. Filter. Okay. So as I say, probably your knowledge gap challenge is widening. Right? That is only thing that you could see as an individual. Okay? We will come to that in a moment. So in data processing stage, we have some problem. Okay? How easy it is to get high frequency data, like high frequency sampled data in an actual setting. For example, in a motor used in a plant, is it easy to get let's say 3600 hertz sampled line current data? Or what kind of data is easy to get? Can you get RMS current or can you get sampled current? Which is easier? RMS current. So the real world data set might be in a very different form than what you might be collecting. And so your data that you are collecting in the lab and the processing you are doing might not be even realistic. Okay, so you have to think from that perspective. So the next step is our favorite. Feature extraction. Assume you have collected good quality raw data. What features would you extract out of it? How would you know that? How to select features? So you can try different things, but that is only trial, right? You are trying different things based on literature. So how to decide this? So this is again the knowledge gap that some of you are mentioning, the depth that we might not be having at this stage. How to decide? As I said, once we are converting or treating everything as data, we don't have to worry about the physical meaning, right? We can add a voltage signal with current signal. We can manipulate it in many ways. So features can also be of infinite order then. So how many dimensional features we need to choose, we do not know. Whether we should have 2 features or 200 features, we have no answer. Right? So the first 3 steps of any machine learning model are these. And we already have identified technical challenges that are so many. Then if you go into a specific model like ANN, obviously you have technical challenges like choosing hyperparameters. You can do, how do you set the layer size? How do you decide on the number of layers? Okay, so there are many questions. What is the computational resource you have access to? Do you have a high-end computer? Do you have just a microprocessor? What is that you are planning to work with? Right? So there are many things that you will have to look at. So all I'm trying to say is these challenges that you identified are very much real. They are real. They exist. I'm not saying no. But even if you overcome some of your identified challenges, the problem does not end there. The problem starts there. Okay? So money is a challenge, but you can go on fundraising. You can get funds. Okay? You can raise funds. But if you have money alone, you may not be able to address technical challenges. So the knowledge gap is the biggest problem we may have to address at this point in time. So what I'm trying to say is, if you think about the steps involved in machine learning, there are 4 major steps. And in each step, we have challenges, technically speaking. Okay? So I would be not utilizing this opportunity because all these challenges are real and existing, and I'm also facing them. So I would be wasting a great opportunity to identify the solutions if I leave you today. So what I'm going to do is I'm going to take your help, and I'm going to make you, so you are nicely seated, so you're going to go into 2 groups, one on my right, one on the left, and you now know some of the technical challenges. Okay, so don't worry about the non-technical challenges like time, cost, all those things, but think from the technical challenges. So I will restrict because there are only 2 groups. So what I'm going to do is I'm going to give you some time. So one of you is going to focus on data collection, like quality, real world like data collection. That is the technical challenge. I want one group to identify, brainstorm, and come up with solutions. Okay? So what you are going to do is you are 7 people. You 7 have come up with some ideas in what way you think It may not be even feasible, that is okay. We are looking into the future now. So we are looking at the opportunities now. So what way you think can these challenges be addressed? So the challenge that you are going to work with is how to get high quality data, assuming you remove the constraints like experimental setups, availability, cost, all those things. How can you get high quality data? Okay. Simulating the real world. And on this side, you are going to look at the problem of feature extraction. So how can you address this problem? When you have data, what is the best way to address the feature extraction problem? Okay. So what I want you to do is go into a group. You are welcome to look up internet, search, okay, all those things. So it's 3:40 almost. So we are going to give you 10 minutes, 10 to 12 minutes each group. Identify, and then there will be 2 whiteboards. So once you have identified, at the 15th minute mark, I will invite one of you to come and write down some of the solutions you have identified. Okay? And then we will reconvene. So 12 minutes for discussion, 3 minutes for writing. So 15 minutes activity. Is that clear? So it's just brainstorming. You are going to come up with some solutions for this problem. And I am going to take picture of these solutions and go back happily. Okay, so you can get started.
Quality as opposed to as possible. Okay. Think of ways that even bring your mind is looking even at a practical stage. So it's brainstorm because that's what the process and then it makes more sense with realistic then it's a market and backside so you can use it. First, we are actually warming up our minds. Like we are like behaving like induction water. Starting time. Yes, but like that's weird. Capacity is not working. First to start on that, capacity is not working. That's for
Index no.
experience in my averaging into very variety of the so like maybe like maybe practice even more than that like case even it's even more than that loading is very much that's why it's
Industries are using dynamics, practical industries. Dynamometers loading expenses. So that's maybe yes, they will be checking different vehicles. How they are checking the vehicles? Something for changing vehicle is engine for EV. How they have research that then we can very practical loading similar as this. Yes, they are using for even very high power. That's one possibility as well. That is only they are having that what that's all. We can change the pattern. We can change the we can change the
appropriate like that maybe the vehicle many other like maybe
Pressure sensors, uneven, even through stability, pressure incorporate the fault. Actually happens parametric pressure, how to imitate the fault. That's what the data collection based on the data depends on how we are in the fault. Actual fault prediction after if I am here with the fault, proper place, proper testing, better selection and place.
Data storage, data pre-processing.
Distance and relation. There are no some sensors.
Automate data collection and quality analysis.
So in 2 minutes, you are going to go to the board and at least write one solution.
Become 6 theoretical data, related data, simulation data, experimental simulation. Simulation is from design, software, real time. No, there is no check. Whether it is matched up or not. No testing, check the quality of the meters. How to check the quality of the meters? We have some. It's written in the letter. Let us distribute data collection for different speeds. Different loads. Load will be different, but the speed is also different. So the load may be given at speed torque already. So no, I cannot write it. I had written in the last. My rating is Madam will come, sir. 1:1 explanation, 1:1. That's good. Time to showcase your it's not response. Madam, right? Which one? Big size. Madam, right? Big size. It's not visible. Can you discuss, madam? It's not visible. Madam, increase, madam. Erase. అంటే ఇక్కడికి కనిపించట్లేదు కదా, అక్కడ లాస్ట్ కనిపించాలి కదా. ఇలా రండి, ఇక్కడ పెళ్లి మార్క్ ఇలా రండి. పెళ్లి ఇలా రాయండి అంటే ఇది బెస్ట్ మీరే రాయండి దాని మీద వాడాల్సింది మీరే. డార్క్ మార్కర్
Yes, we are going to look into the solutions in a minute. So you will take a group picture in front of your board at the end of this session. Okay, as an amen.
Madam, data collection, technical solution. Technical solution. Technical solution. Right.
Okay, last 1 minute, then we are going to sit down and debrief, kind of discuss some of the solutions that is available in literature. Not working, you can borrow from that's all. So you may have to borrow, you don't even marker.
It's also like
That's fine. Okay, please settle down. You can sit wherever you want. You can sit. Please come back to your original position.
Okay, last 1 second. No, it's time up. Okay, so that's fine. You can just settle down. Thank you so much for this activity. I know this is kind of new to you all. That's what I realized. So probably I should have guided you better in terms of the activity itself. Okay. So on the left-hand side for me, we have some of the solutions for collecting high quality, close to real world data. On the right-hand side, we probably have some solutions for solving the problem of feature extraction and how to decide on what features, right? So I'm not going to debrief this because that is not my intention. We probably it's good to do it casually, we can do it, but I'm not going to do that now. What I'm going to do is I'm going to present to you what is available in literature. Okay, so when it comes to the problem of how to generate data from simulation or from experimental test bench that is close to real world, the solution that researchers around the world are trying for is what we call as a digital twin. Okay, so therein lies your opportunity as a researcher. So current research of digital twin for predictive maintenance is at its initial stage. So if you have started your PhD or if you're in the first year, first 2 years, you can explore this field aggressively. For those of you that are in masters or about thinking about higher education, this is a field that will have immense opportunities. Okay? Actually, I have given a QR code for MATLAB website and they talk about digital twin, but the idea is you create a twin of your real world setup. Okay, a twin will behave exactly like the real world setup. And how do you create this twin? You have two different approaches. One is what we call as a multi-physics model. That means you try to model the thermal behavior, you try to model the electromagnetic behavior, you try to model the mechanical behavior, you try to model every domain, physical domain behavior in single model. Okay, that is what we call as a multi-physics simulation. A commercial tool like ANSYS, MATLAB, they all have these capabilities to develop multi-physics models. Okay, so that is one approach. But the approach that is becoming more popular in recent times is actually use of generative models. Okay, so if you have heard of ChatGPT, so generative predictive transformer, right? That is the GPT. So they are using generative transformer models to synthesize data that could be close to real world. Okay, so researchers are trying in both sides, like multi-physics as well as in data-based techniques, and probably there are some researchers trying to combine them both. They are developing a model which is a multi-physics model. It gives you some data and then you use it to generate more data like that. So the field itself is still nascent. It's just a few years, and therefore this is a great opportunity for you all if you want to pursue research in this domain, there are some excellent problems where not just you, but the entire world has the knowledge gap. And we just need people like you to find some solutions. Okay? So this is one opportunity. The second problem we have is how can we minimize the impacts of feature selection, right? So the problem is how do we mitigate, right? That's the question. And the solution that researchers have come up with is something very interesting. They say, why should we do feature selection? Why can't we have a model that chooses the features? So the idea is people have started choosing methods. I will be presenting about one of the techniques in tomorrow's session. It's called convolutional neural network. There is also a technique called long short-term memory based algorithm. There are also generative models that are being used. Okay, transformer model especially is very gaining popularity in these aspects. So what we are trying to do is we are trying to capture raw data, feed it. We don't bother about feature extraction. Reason being, we think that that model can identify features which are not even visible to us, which we cannot even conceive. The model is going to conceive. Because it's only data, as engineers, we will never be willing to add voltage and current. But that model will not hesitate to do that. Okay? And probably that might result in better accuracy or better performance in lower training time. Okay? So there are two complex problems, and research around the world is taking paths that are just starting. Okay? Digital twin is one domain, and using deep learning typically, or specialized networks or specialized algorithms for overcoming the problem of feature selection. Okay? So these are the two broad themes that from a technical perspective research has started. Okay? So if you are keen on pursuing research in this field, which I would strongly encourage you to, you are welcome to look into these aspects. Now, the good thing about researching on these fields is they are transferable skills, as we will call it in an industry. So if you learn how to build a digital twin for an electric motor used in an EV, you can be employed by any company that wants you to build a digital twin. You just have to put in the effort to build a specific digital twin for a particular company. Likewise, if you are working on CNN and LSTM algorithms, you may be using it for any particular application later on. It need not be only condition monitoring. So these skills are extremely transferable, and therefore there are lots of opportunities in this domain. Okay? One of the reasons I didn't want to debrief is because this is the first time I see you all are even doing a brainstorming activity. So that is why I did not debrief, but typically at the end of the brainstorming, there will be a debriefing meeting. Okay. Okay. So some of the points that came up, how can we address knowledge gap? We are like any ANN algorithm that is to be trained, right? We have to continuously update ourselves. Our weights and biases have to be continuously updated. So there is no other mechanism. So continuous learning and constant input is the only way we can minimize that knowledge gap. Knowledge gap will always exist. Another way is to collaborate, right? So if you are good at something and if your friend is good at something else, then you kind of work together to minimize the gap. So those are things that you will have to explore. These are not technical issues. These are some things that you will have to look into as an individual, as a society, as an organization, all those things. How can we mitigate expenses? I think this forum, the GIAN workshop, has brought in researchers from all around the country pretty much, right? And in fact, if you include me, from many parts of the world as well. And now we have made a connection. So the best way to mitigate expense around the world is researchers generally what they do is they collaborate based on the facilities they have easy access to. So for example, NIT Warangal has a center of excellence where they can machine and create that eccentric bushing for you. Okay. So it will be much cheaper for you to travel from Hyderabad to NIT Warangal than to actually set it up in your own institution. If you think about it. Okay. So that is the idea. So you have a setup here, you can collect data. And one thing that I want you to remind you all is most of our undergraduate machines lab already have enough equipment for you to start working with traditional machines. May not be permanent magnet machines, but at least traditional machines like induction motor. Many of the older labs will have an open winding induction motor. You can tap into different taps and you can say create an asymmetry and check. Right? Your modern oscilloscopes have storage capabilities. Your modern microcontrollers, which are extremely low cost, are good enough to do A to D conversion, store data. Okay? So you have many facilities already available at your hand. It is just a matter of you trying to think outside of the traditional boundaries and come up with test benches. And the thing is, we should not think like an academic person when it comes to experimentation. We have to think like an industry person. That resource is time constrained. So if you can do your experiment in 3 hours, all you have to do is seek permission to have that facility for 3 hours. Right? So it's up to you to convince whoever that needs to have access to a particular test equipment for 3 hours. Okay? So it is not, so what I'm trying to say is, it is not as bad as you think. You already have access to many of these equipment. And if you know, say for example, if you have from NIT Warangal, if you know another NIT or another IIT has a PMSM motor drive, as I said, it will cost you much lower to go to that institute, get the data and come back. Than to invest in your own dedicated setup. And this is true for private institutions too. It's not only for government institutions, right? You don't have to rely. So the answer is collaborate. And this is strongly encouraged around the world. It's not a new thing that I'm saying. Government grants are given like that. When they encourage collaboration between researchers. Government does not want the same test setup to be replicated in every institution. Okay? They want one center where people can go collect data and then people can use it. So that is the intention. So in summary, we are nearing the end. I am giving some time because I want to take group photos with these boards. In summary, in every step of machine learning algorithm or method, we will face a challenge: data collection, data processing, feature selection, hyperparameter tuning, like that. There is lots of unknowns, uncertainties to overcome. But in every challenge, there is an opportunity. So if you are willing, there is a way. Right? So it's a matter of your will. And just to recollect, what is PhD? So you are either doing it or you have done it. So you just have to repeat it. Right? So with that, I will stop this session. We can casually debrief and take some pictures. And then we will meet again tomorrow morning around 9. Does that sound good? I have actually shared research articles and QR codes. I encourage you to read the introduction section of that research article I shared. That gives you an idea of how trend is going towards mitigating features or collecting data like that, especially with respect to a data-based, machine learning, algorithm-based approaches. Okay, so you please read through the introduction section. You don't have to go through the entire paper. That will give you a very good idea of what you should explore as a researcher. Okay, thank you so much.